All right, I think we can go ahead and get started. Hello and welcome to the second event in our 2022 Alaska Sustainable Energy Conference virtual workshop series called Going with the Flow, Ocean and River Energy in Alaska, sponsored by the Alaska Center for Energy and Power. I'm Gwen Holdmann. I'm the director of the Alaska Center for Energy and Power, which is an applied energy research center based at the University of Alaska Fairbanks that focuses on research that's specifically relevant to Alaska's communities and industries. I'm actually really excited about this workshop because hydrokinetic energy is the first research area that we actually stood up specifically in terms of building capacity around for the University of Alaska Fairbanks. And the reason was because there was so much interest for our communities in taking advantage of water flowing down our rivers and in our tidal and wave resources in the state. And since the vast majority of Alaska communities are located on some sort of body of water, the interest in tapping those resources became very significant when we had some early price spikes around 2008, right when the Alaska Center for Energy and Power was formed. And the interest was high. There was a couple of early pilot projects that were developed on the Yukon River around that time, including by the Yukon River Intertribal Watershed Council and Ruby and Alaska Power and Telephone in the community of Eagle, Alaska. And both of those ran into a lot of challenges that weren't necessarily anticipated, related from everything from mooring the systems to debris mitigation and concerns related to fish population impacts, potential fish impacts. So we stood up this research program at the university that brought together researchers from different colleges and institutes around the University of Alaska system, and then partnered with the private sector and other universities to pretty systematically address some of these issues. So thanks for joining us today. I really view this as an opportunity to sort of review where we've been historically and where we're going in the future. This is part of a series of 4 different workshops that are held monthly as 2 half-day Zoom sessions, just like this one, free of charge, leading up to the Alaska Sustainable Energy Conference, which is going to take place May 24th through the 26th at the Denina Center in person in Anchorage, Alaska. The first virtual workshop was nuclear energy in Alaska, which was held last month in February. And our next 2 virtual workshops are hydrogen in the high north, looking at decarbonization of fuel supply, and then electrify everything will be held in April. Those will be in April and May. So please visit the website at Alaska Sustainable Energy to register for those workshops if you're interested in those. You had the option when you signed up for this one as well to register for those other workshops. This particular workshop is going to include presentations from 15 panelists over these 2 half-day sessions who've been working on different aspects of ocean and river energy. And so they'll be sharing their knowledge and expertise. We really appreciate the time that they're taking to participate here today over the next couple of days. So anyhow, we've got the agenda up on the screen for you to see for today. The way that we're going to have this formatted is each panel will be moderated by a moderator, and then we'll have a following Q&A between our attendees and our panelists. Before we start today, we thought it would be fun to take a look at where our attendees are joining us from today. And so there's a poll that you can participate in. We'd like to ask you to please participate in. You can see that in the chat. You can click on that link. And I think it's on the screen here as well. So can just kind of drop into the map where you are joining us from today. All right, we actually have a world map here today, and I have not seen this map yet. So I expect we'll have, looks like from Alaska and Canada. So I will be honest and admit that I am the one that is in the middle of the Pacific there in Hawaii today. We're working with the Hawaii Natural Energy Institute here, working a little bit on a few areas of common interest between Hawaii and Alaska. So I am not in the state of Alaska today. All right. So I can certainly see our partners at the UW and OSU are also represented on that map. So thank you for sharing that. we'll have a couple of other polls as we go along too, just for the fun of it. So a few housekeeping issues or things that we'd like to go over. First, please introduce yourself in the chat. The chat is open, everyone can see that. So please introduce yourself. We're not going to have time to do that. So please make sure you kind of let folks know who you are and where you're joining from and what organization you represent, if that's appropriate. And if you're having any difficulties with audio or trouble viewing the presentation, there's an event support. You'll see that as one of the participants, and you can go ahead and contact them and they'll help you directly. So during the workshop, all the attendees will be muted, so you won't be able to speak. So you just can use that chat feature, but you can go ahead and submit questions or comments using that chat feature at any time during the presentations, and then the moderators will go through and kind of read those questions to the panelists at the end of each session. So drop those in as they come up so that the moderators can be prepared to ask those. The recording of the workshop is going to be available afterwards on the Alaska Sustainable Energy website. It's going to be available there about a week or two out. We're hoping to have as much concurrent participation as possible. So just check back for more information or check in with us and we'll get you the link, but it'll be on that website at a later date. And so with that being said, I would like to introduce and welcome Curtis Thayer. He's the Executive Director of the Alaska Energy Authority, and he's going to share a few opening remarks. Thanks for joining us, Curtis.
Thank you. Sorry, let me get adjusted here a little bit. Thank you, Gwen, for that introduction. I currently serve as the Executive Director of the Alaska Energy Authority, and I really appreciate you tuning in for this week's workshop on Going with the Flow Ocean River workshop hosted by ACEP, and to explore the ocean and river energy resources. AEA has enjoyed a long, productive partnership with ACEP, and we're pleased to be part of this discussion leading up to the first Alaska Sustainable Energy Conference in May, coming up very quickly. A little bit about AEA. AEA is the State Energy Office and lead agency for statewide energy policy and program development. Our mission is simple, is to reduce the cost of energy in Alaska. And there are several ways we go about doing that. We're involved in power generation and transmission on the rail belt with an interconnected electrical grid from Fairbanks to Homer. AEA owns Bradley Lake Hydro Project and the Alaska Intertie, the largest hydro and transmission projects in Alaska. During the last 20 years, AEA has designed and constructed more than 90 powerhouses in rural Alaska, most of them diesel powered, although some run primarily on hydro and others integrate renewables such as wind and solar. AEA's experience with the design and construction of the power generation, transmission, and distribution heating systems all over Alaska prove valuable in analyzing the potential of ocean and river hydrokinetic energy resources that contributes to Alaska power needs. AEA has been engaged in Alaska's hydrokinetic development in several ways over the last 15 years. We organized the first Alaska Tidal Energy Conference in Ketchikan back in 2007. We partnered with the Alaska utilities and other stakeholders and the Electric Power Research Institute to produce several reports. Tidal In-Stream Energy Resource Assessment for Southeast Alaska, River In-Stream Alaska Conversion Characterization of Alaska Sites, and the 2019 Renewable Energy Atlas with REAP, which includes tidal resources data that is available on AEA's website. AEA has presented numerous times on wave and tidal energy at the Alaska Forum on the Environment. AEA administers the Renewable Energy Fund, which has awarded several grants for hydrokinetic projects, including the Igiugig Village Council for their feasibility and conceptual design. At present, AEA is supporting efforts to integrate ORPC's Ocean Renewable Power Company's RivGen system in Igiugig for upgrading the powerhouse switchgear. As we look to the future, AEA will be monitoring the hydrokinetic progress in Igiugig, Yakutat, and other states, and is looking for opportunities to apply lessons learned to the potential hydrokinetic sites in Alaska. And I think it's important to note there's two programs that we have. We have what we call the Renewable Energy Fund, which awards grants up to $1 million in various rounds. We just closed our latest round, have several hydro projects in that round, and we have 39 applicants and $15 million. of grant money. And in addition to that, we also provide a power project loan fund where we can loan up to $5 million in-house before going to the legislature on various energy projects. One of those projects happens to be Halong Nai on Prince of Wales Island. We've actually have $27 million invested in that project, $20 million in a loan, and it provides 100% of Prince of Wales energy needs. But in conclusion, with thousands of miles of coastline and more than 12,000 rivers, streams, and creeks, Alaska has some of the greatest potential for ocean and river energy resources in the United States. While hydrokinetic energy has promised for the state, it has quite a few challenges as well. AEA will continue to study with the hopes of identifying potential hydrokinetic power generation sites in Alaska. And with that, I'll turn it back to Gwen. And again, thank you for allowing us to participate today.
Thank you very much, Curtis. And I absolutely agree. We've had a really fantastic partnership over many years in this technology space. And we look forward to continuing to partner with Alaska Energy Authority in this area. So now I'd like to introduce Jeremy Casper. Jeremy is the Deputy Director for the Alaska Center for Energy and Power of Research. And he essentially oversees all of our research programs and teams, including solar, power systems integration, beneficial electrification, and all the other research that we do. Our research team has somewhere between about 55 researchers associated with it today, so it's grown quite a bit since Jeremy joined, which is about 6 years ago when he joined as research faculty and specifically to help run our hydrokinetics energy research program, initially serving as deputy director and then full director for the last several years. So anyhow, Jeremy's going to be sharing the purpose and the goals of this workshop, and he's going to be serving essentially as the MC for the event. So Jeremy, I'm going to turn it over to you to kick us off here.
Great, thanks, Gwen. First, I'd like to thank Gwen and Curtis for kicking off the meeting. I think you'll see we have a great cross-section of speakers ranging from technology entrepreneurs to university and national lab researchers and Alaskans who are intimately involved with projects in the state. Each session should allow plenty of time for questions, discussion, and interaction with the panelists. So please get your questions ready in anticipation of the chance to ask everybody where they think the technology is and where do you think it's heading. So the overall objective of the workshop is to give Alaskans a chance to get up to speed. As Curtis and Gwen mentioned, there's been a lot of interest in this technology in the state, going back about 14 years now, so predating my participation in the area. And we've seen a number of deployments and we've seen a number of challenges crop up, but I think we're getting to a place where we have solutions to some of those challenges and we can move things forward pretty quickly. So I think you'll see that from the presentations today that we're in a good spot. And part of the genesis for this meeting was there was kind of a resurgence in interest in the state in marine energy. As Gwen mentioned, back in 2008, 2009 timeframe, there was a big interest and the industry was kind of in its new phase. And now we've gotten to the point where the industry is getting more mature. We're addressing some of the problems and we're starting to move into the deployment phase. So I think you'll see that reflected in the speakers today. So we'll also have, in addition to some of the presentations from the developers, we'll get to see some of UAF's latest work on project economics and then looking at how you integrate these technologies into microgrids. So basically 2/3 of the communities in Alaska have islanded microgrids on that order. And so that's going to be a big challenge in how you use the technology in the state. So we'll get a little bit of update on that. We'll also hear from some of the national labs on their work on resource assessment and then regulatory challenges. And we'll hear from Alexandra Salmon from the Igiugig Village Council, where they have the RivGen project. We'll also have a few videos highlighting some of the fisheries work that we've been doing here at UAF. Unfortunately, this meeting conflicts with the American Fisheries Society meeting, so our fisheries biologists were not able to break away from that. So we will feature some videos of what they're up to, as I know that's an important question for Alaskans. Day one will focus on current energy converters. So for So tidal and river energy converters, while day 2 will focus on cross-cutting issues. So issues that are common to both current energy converters and wave energy converters. And sorry, I'll just give you a heads up that I'll be using, hopefully not too often, but the terms KEX and WEX. So current energy converters and WEX, wave energy converters. I will try not to do that. I'll try to spell it out, but if I do that, slip into that jargon, I've hopefully given you an intro so you can follow along. So the day 1 will focus on KEX, current energy converters, for harnessing river and tidal energy, while day 2 will focus on cross-cutting issues, regulatory issues, grid integration, and then community perspectives. The first panel of day 2 the final panel on day 2 will get us up to speed on where wave energy converter technology is, and then feature some results from the University of Hawaii's testing site, actually pretty close to where Gwen is right now. It's called WETS, the Wave Energy Test Site. And then finally, we'll wrap up the workshop with a chance for the panel moderators to sum up their thoughts and field a final round of questions. We'll have some more interactive polls throughout the workshop, so please participate in those. Super helpful for me to see where folks are dialing in, and then find out kind of the level of knowledge that you guys have. So finally, the sessions will be recorded. So if you know folks who are interested but unable to attend, a video of the workshop will be available after the fact. So before we dive into our first panel, here's another interactive poll. And if you can go participate to that on the, follow the link and participate, we'll give it a minute and we'll get see where people. So the question is, how many current energy converter deployments have there been in Alaska? Looks like we're getting some good responses, and I'll give it another minute, and then we'll move on to the next one. Okay, so looks like we had some pretty good responses. We had, for answer A, we had 1 deployment, 2 to 3, 4 to 7, and then more than 8 was that final answer. And if you were listening to Gwen, you heard she listed off some of the initial deployments. There was early on in 2008, the Yukon River Intertribal Watershed Council had a deployment in Ruby, Alaska. That, I think, year after that, or maybe 2 years, there was one in Eagle, and then following that, there was actually one, not too many people know about this one, but there was one in Tanana, Alaska. So the manager of the power plant there actually built his own river energy converter and had it going, connected up to the grid. And then, so that was 3 of them. And then everybody, you'll hear a lot about the RivGen project in Igiugig, so that's number 4. And then maybe you probably don't know, but UIF has actually hosted at least 4 turbine deployments, if I'm counting correctly. We've over the past 5 years or so, we've hosted one by Blade Runner, we've hosted one by the Waterhorse technology, and we've hosted a couple of others in there as well. So we're actually up to over 8 deployments in the state of Alaska. So pretty impressive, considering there actually haven't, worldwide number of river energy converter deployments is pretty small, probably under 20, I would say. That's a rough number, but we've got a lot of those have been in Alaska. Okay, so thanks for participating in that. With that, we'll lead into the first panel. So we'll hear about, in this panel, we'll hear about kind of the resource in Cook Inlet. That's kind of the big elephant in the room. And then what some of the challenges are. And we'll learn about upcoming technologies that UAF is working on and our partners in the private sector. And then we'll hear about how to potentially assess the suitability of sites on the Kuskokwim River as well, using pretty limited information. As a reminder, during the session, questions can be submitted via the chat box, and we'll address those as best we can during the Q&A following the panel. So with that, I'd like to hand it off to our first moderator, Dr. Shana Hirsch from the University of Washington.
Hi, everyone, and welcome. Good morning. My name's Shana Hirsch. I'm a research scientist at the University of Washington in the Department of Human-Centered Design and Engineering. I'm also an associate director of the Pacific Marine Energy Center at the University of Washington. I'm excited to be here today to kick this off with the first panel, which is going to be about current energy converters. We have 3 speakers for you. Each of them are going to have about 20 minutes, and then we're going to reserve a good amount of time at the end for questions. So please do write down your questions, keep them at hand, or put them in the chat right away and we'll collect them. So let's get started here. First off, we have Levi Kilcher, who's a senior scientist at the National Renewable Energy Laboratory. He leads the Marine Energy Resource Characterization Project for the U.S. Department of Energy's Water Power Technology Office. He also has a PhD in physical oceanography from Oregon State University and is an expert in tidal processes, ocean turbulence, and surface waves. He's a contributing author to International Electrotechnical Commission Standards for Resource Assessment and Power Performance. Early in his career at NREL, he also supported technical assistance in several rural Alaskan communities. He was born and raised in Cook Inlet, Alaska, and he has a strong personal connection to the ocean, a pragmatic understanding of opportunities, and the inherent challenges of marine energy. He's passionate about identifying local renewable energy options that meet cultural, environmental, and economic needs of communities of all scales, and he believes marine energy has a unique and impactful role to play in the energy economy of the future. So let's hear what Levi has for us.
Hey, everybody. Can you see? Hopefully you can see my screen here. There we go. All right. Thank you for that introduction. It's my pleasure to be here. And yeah, like Jeremy alluded to, I'll be talking about some resource assessment measurements we made in Cook Inlet earlier this last summer, in the summer of 2021. This photo was taken from the tip of the East Foreland, and you're looking, I apologize about that laser pointer jumping around there. You're looking east across Cook Inlet at the West Foreland is there in the distance. And you can see Mount Redoubt is looking really spectacular. I apologize. I don't know what's going on here. And you can see a couple oil platforms there in the inlet. And the other thing that you can see in this image is the tide rip there in the foreground. The flow is moving out the inlet to your left. So we're ebbing at the moment. And I think that tide rip indicates just how strong the currents are here. And you see, I think you see that basically on ebb and flood, 4 times a day. So here, I think everyone probably who's on this call is familiar with Cook Inlet. This is my sort of picture of the resource in Cook Inlet. So this the red colors indicate the most intense velocities in the inlet. And so we looked in our measurements this summer, we took a look here right at the tip of the East Foreland. We were interested in this spot in particular because it's directly adjacent to the transmission infrastructure of the rail belt, and that obviously delivers power to 70% of Alaska. There's a electrical substation, high voltage substation within just a few kilometers of the tip of the East Foreland. So I think that, you know, as you think about building this site out in the future, there's existing transmission infrastructure. And the other thing that's really interesting, in my opinion, about this site in terms of when we're talking about renewable energy of the future, is that the Agrium nitrogen urea production facility is located right here at the tip of the foreland. And ammonia, which is sort of one of the things that's produced in the process of developing urea at this site, is one of many renewable fuels that people talk about as being a potential option of the future. So there's, to me, this the fact that this Agrium facility is right here, you know, sort of begs the question, is there a potential opportunity in the future where you're either producing e-fuels and from tidal power, or maybe you're just using tidal power to supplement the electricity needs of urea production, and then you're able to sort of sell that urea as like a renewable energy supported product. Another thing that I just wanted to point out is, you know, NREL just completed this RPS assessment for Alaska's rail belt, and tidal energy was included in 2 of the scenarios, scenario 4 and 5. And, you know, the contribution from tidal in this model is relatively small for 2 reasons. One is that, you know, tidal energy technologies, current energy technologies, are at a relatively early stage of technology readiness. And there's a long way to go from where we're at now, from having a few, and there's going to be other speakers who talk more about the details of the technology. So I'm just giving my perspective. But where we're at now of having several different technologies that are showing success in single device deployments, and then sort of on timescales of a year or 2, maybe a few years, these technologies are proving themselves, to having something that's fully commercial where the costs are low enough to enter the market. And we've seen, you know, a decade or 2 of deployments of many of these devices to demonstrate that they're commercially ready. And so I think one of the things that we at NREL have been advocating for is the idea that we're ready to start making those, doing those large scale tests of multiple devices. But the reality for this study was that it, you know, tidal's not quite at the stage yet where you can say, okay, there's going to be, you know, 400 megawatts of tidal energy is sort of a feasible thing. So for the 2040 timeframe that this was looking at, 50 and 75 megawatts of tidal energy seemed like sort of reasonable starting points. The second reason that tidal didn't show up has to do with sort of transmission, it didn't show up larger than it is in this study, has to do with transmission limitations and getting that power, you know, off the Kenai Peninsula up to the Anchorage and Fairbanks where, you know, where there's larger power demand. And so, you know, if in the future the state were to build out larger transmission infrastructure, then I think you'd see a greater opportunity for tidal to contribute to that. Here's a slide about the resource measurements. So here we're looking right at the tip of the East Foreland, and we made a bunch of different measurements. We had 2 moorings with upward and downward looking ADCPs. We also had a bottom lander on the bottom of the ocean, looking upward, measuring the currents. And then we also did transects back and forth across the channel using the boat. So we had a downward looking instrument. For those of you who aren't familiar with ADCPs, that's here in the upper right corner. This shows the, these instruments are totally amazing. They send out acoustic pings and they listen for the Doppler shift the echo that off of particles in the water column. And based on the shift in the frequency that these things hear, they're able to measure the velocity of the water throughout the water column. They're totally cool things. I could go on and on about them, but basically these are the instruments that allow us to measure the velocity in the water column. So here's just a really quick overview of the data that we collected. The plot in the upper left there indicates the depth average currents are indicated by those red arrows. So this is basically during peak flood, and you're seeing currents between 2 and 3 meters per second flooding to the north. The orange dots indicate the location of the moorings, and the green triangle is the bottom lander. And then the bottom panel shows you sort of the vertical structure of the currents across that channel. So red and dark red indicates, strong currents to the north. The Q is a volume flux estimate. So that's sort of like the total volume of water that's moving through here. That's really important for calculating sort of total power that you could generate at this site. And then the tidal amplitude plot is there. That shows you the blue line is when we made these measurements. So we made this transect was made just a little bit before high tide. That's when the peak flood currents occur. And then as we step forward in time to the next transect, now we're a little bit just almost on top of high tide. You see the currents are weakening a little bit. And then as you step forward in time again, the currents are becoming much weaker just a little bit after high tide. And then here about 40 minutes after high tide is when we actually see the slack condition, the slack current condition. Stepping forward again, now the currents are starting to reverse to the south, starting to ebb out of the inlet. And then a little bit as you approach low tide, then you see the peak ebb currents. And we can step through, and as we make more transects back and forth across the channel, we get back to the peak flood condition. So that's just sort of a nice visualization and step walkthrough of the currents at this site. These volume fluxes, these 3 meter per second currents that we're seeing are really premium tidal energy resource. So basically we are seeing the really energetic resource that we had hoped and expected to see at this site. And so I think it's really promising for tidal energy development at this site. This panel shows the data that we got off of the bottom lander. So now the top panel shows the tidal elevation. So you can see we have 2 months of data. This is just a totally phenomenal data set. The currents, especially during spring tides, are well over 3 meters per second. And then the bottom panel shows some of the turbulence data that we were able to collect. And turbulence is really important for designing these turbines, because we learned in the wind industry that, the wind industry in the 90s, especially, turbines were breaking down earlier than they had sort of expected them to. And they figured out that turbulence, basically shaking the turbines, was causing those early failures. And so they sort of went through a process of redesigning them to make them more robust. So we're working on leveraging that experience to measuring turbulence early on, so that we can give that to the technology developers, so that they can design their technologies to account for turbulence, so that we don't have to learn that lesson the hard way later on. Is a big piece of what we're doing here with these measurements. And here's a zoom in. This sort of 60-day view is like, it's kind of hard to actually see what's going on. So I'll zoom in here. We've now have like the depth averaged currents in this upper panel in the red and the blue. And again, you're seeing the depth average currents, especially during spring tides in the flood direction, over 3 meters per second. You can see the vertical structure of the currents here, and then the turbulence again on the bottom. And those turbulence levels, especially near the bottom, are really intense. If we look at this in a depth averaged sense, sorry about that. In a time average sense for different levels of flood and ebb. So red lines are for flood, blue lines are for ebb, and then these gray sort of lighter lines are weaker current conditions. But basically what you see here is that the strongest flood currents are well over 3 meters per second. The ebb currents are well over 2.5 meters per second, approaching 3 meters per second. And then if you calculate that in terms of power, there's a cubic relationship between the power that you get out of these currents and the current speed. And so you see those strong floods really provide a lot of power. So you're seeing almost 25 kilowatts per square meter of tidal energy flux at this site. And then the last thing is this turbulence intensity plot. This is a metric that we use just as sort of a basic understanding of turbulence at these sites. And it's really low, especially above like 20 meters from the bottom. So above 40 meters depth, the turbulence is all below 10%. And that's really good. You know, in the wind industry, they frequently see turbulence levels of 15%. So, you know, I think the idea here is that the ideal depth, in my opinion, for turbines is this like 40, you know, below 10 meters, I think, because you want to be below the ice, I would assume. And you want to be below ship drafts and those sorts of things, but you probably want to be above, you know, 40 meters depth, because that's where you're really going to capture the most power and have the lowest turbulence levels. But obviously, you know, different technologies have different approaches to this. So, you know, that's just sort of my opinion on if I were designing devices, that's the depth range that I would target. The other thing that we did when we were out there is we measured the sediment. And this, you know, I think for anyone who's familiar with Cook Inlet oceanography, you know, spends time in the inlet, there is a lot of sediment. We measured 0.5 kilogram per cubic meter of sediment. And so I think anyone who develops a project here is going to have to figure out how to design technologies that can survive in this kind of very high sediment load concentration environment. That's about it. You know, like I said, this site is a really amazing tidal energy site, in my opinion. You know, we typically look for at least 2 meters per second currents for what would be considered a good tidal energy site. Sometimes 1.5 meters per second, but here we've got well over 3 meters per second is the peak currents. You know, again, that ideal depth range and having that low turbulence there in the middle of the water column makes it a really great site. Again, the high sediment load is something people are going to have to deal with. And then just sort of as a really crude estimate of if you built out a project here, you know, and you tried to capture some of the energy in this blue box, there's about 150 megawatts of like kinetic energy flowing through that box. And so if you tried to capture half of that, and your project had a capacity factor your technology had a capacity factor of about 0.4, which is sort of a realistic capacity factor for these technologies, you know, you would have an array capacity of 150 megawatts. So that's just for this site. You know, the important thing that I want to point out is that here at the East Foreland, I think is a really promising early site for these technologies to demonstrate that they to develop experience and demonstrate that these technologies are robust. But the west side of the inlet, the western half of the channel between the East Foreland and the West Foreland, is where most of the energy is in the inlet. And so as time goes on, the idea would be that you would actually build it out over there. I just wanted to make one comment here on, how long it takes for this for these technologies to become commercial. It took the wind energy industry 30 years to get from, some of the early days in the 80s to where they are now. I guess it's been 40 years now. But, you started to see those commercial projects in the early 2000s. I don't want to speculate too much on where we're at, but we're on the, let's say I think, in my opinion, we're still on the left half of this plot. So we've still got 5 to 10 years at least before you see tidal energy projects delivering power at, competitive with other forms of generation. And a lot of that, in my opinion, has to do with demonstrating that the technologies can operate reliably for long periods of time, and also just doing the R&D that drives the costs of these technologies down. One thing I think is really important as you're doing that is to involve the research community, because I think from what I've seen, the tidal energy, well, any project developer is often so focused on getting their project in the water and making sure it's online and working, that sometimes they overlook collecting all the data that's necessary, whether that's environmental monitoring data or just some of the mechanical engineering or electrical engineering data that's needed to accelerate the technology development and the R&D pipeline. And I think the labs and universities are great partners to support that work. So that's all I've got. Thanks for your time, and yeah, I'm looking forward to hearing from the rest of the panel.
Thank you so much, Levi. We've got a lot of great interaction and questions coming through from the audience, and I'm taking note of all of those, and we're going to have a good amount of time at the end to have the panelists answer the questions. So please just keep those coming, and we'll make sure to get to as many of those as we can. So next up, I want to introduce our next speaker, Eloise Petrone-Brown. She comes to us from the Alaska Center for Energy and Power and the Pacific Marine Energy Center at the University of Alaska Fairbanks. She's a research professional and oceanographer at ACEP and PMEC. Her research interests include ocean waves and nearshore circulation, with a focus on renewable ocean and river energy. So before joining ACEP, Eloise was a visiting faculty in marine and environmental sciences at Alaska Pacific University. And she's also worked with the University of Western Australia and NOAA. She's studied oceanography and has an MS from the University of Alaska Fairbanks and a bachelor's in environmental studies from the University of California at Santa Barbara. Some of her recent projects have included practical resource analysis for hydrokinetic river energy conversion, which is REC, R-E-C, on the Kuskokwim River in Alaska. And that's what she's going to talk to us about today, as well as resource assessment for wave energy conversion, WEX at Yakutat, Alaska, and oceanographic observations and analysis for the Beaufort Lagoon ecosystems, LTER, as well as erosion on Arctic permafrost coasts. So thank you so much, Eloise, and we're looking forward to hearing what you have to say to us today.
Thank you, Shanna. Let me just share my screen. Okay, can you see that all right? Okay, today I will present our recent work on site suitability of river energy and isolated microgrids on the Kuskokwim River, Alaska. This is a collaborative project with authors from the Alaska Center for Energy and Power at the Pacific Marine Energy Center at UAF, Alaska Pacific University, and the University of Alaska, Anchorage. The idea for this project came from Melanie Wilson, who did her master's project at APU, and several of us were on her committee. We incorporated field measurements that were part of a statewide resource assessment of hydrokinetic river energy resources by Tom Raven to come up with a tool to quantify site suitability for current energy converters, or KEC. Thank you, Jeremy, for explaining that already. So on the one hand, we looked at the hydrokinetic resource. So how much river energy is there? But then what other factors are there to consider? There are social and environmental and economic constraints. And so that's what's meant by practical resource. We addressed some of those and applied our method to sites in Alaska. One thing I want to point out is that we only considered the open water season from June 1st to October 18th, when the river was ice-free. This is our study area on the Kuskokwim River, which is in southwestern Alaska, and the 7 communities we selected. The furthest upstream was Stony River, and then the furthest downstream here was Cow's Egg. So here's a conceptual diagram of our analysis, showing the 8 different factors that we included. What I want you to notice here is that we weighted them by importance. So there's 3 different groups on the left-hand side. Most of these factors are related to economics and costs, and I'll explain each of them individually. At the bottom, we have more social factors, and those were weighted as less important. And in the middle, on the upper right, we have the environmental considerations and the hydrokinetic resource. So I'm going to start by explaining that one. So as part of a statewide resource assessment, transects were surveyed at all of our locations, and thanks to Levi for explaining how ADCPs work. Basically, a transect is like a cross section of the river. It lets you see what the flow looks like. It's a snapshot in time at that one time. So there were transects, multiple transects at each site surveyed with ADCPs. And as part of this study, you can see also our recommended location for a current energy converter at each site. That's what the blue star is. And I'm just showing you a couple examples from Crooked Creek and Antioch. We have a fair amount of data, and so I'm going to try and just highlight a few examples and not go into everything in the amount of time we have today. Now, this slide I put up for the engineers in the audience. I'm not going to go into great detail on the equations. The short version that you need to understand is that there's 3 main time periods. The field data, so the transects and the physical measurements of the channel geometry, where the snapshot in time were taken over the space of a day or 2. Also part of the field data, hobo pressure sensors were deployed for anywhere from 2 weeks to 8 weeks, depending on the location. So we captured discharge over 1 summer during that part of the field work. And then the third time frame is the USGS maintains a gauge at Crooked Creek. And so we were able to get 20 years of data and then relate that back by inputting our discharge from the transects and then our longer term discharge from the pressure sensors. We were able to back out what 20 years, a typical open water season looks like for 20 years at each of the sites. And so we start with discharge, we convert it to velocity, and then the end goal is to back out power. And that is how we're able to calculate our hydrokinetic resource over the whole open water season in megawatt hours over 4.5 months. And the only other thing I want to say on this is the Manning's roughness. That's a way of describing the friction that the water feels at the bottom of the river. And so we were able to tune our HECRAS model for each site. Let me show you what that looks like in a second. For our in order to be able to back out power, we had to choose a current energy converter because you need these parameters to go into the equation for technically recoverable power. So we chose this conceptual design current energy converter that Previzic described in his 2008 EPRI report. It's a floating style current energy converter. It's on pontoons. It's got a 47 kilowatt nameplate capacity. And it has 4 rotors with 2 meter diameter, and each one has a swept area of 3.14 meters squared. And its device efficiency is 34.4%. And those are the 3 parameters that you need in this equation in order to be able to back out power. And those numbers have to come from a manufacturer. So this one is 10 meters wide and it's 50 meters in length, and that goes all the way to the tip of the mooring. And I just wanted to say that we recognize this is a conceptual design current energy converter, and that technology is approaching commercialization. So it was our intention that our methodology was transparent enough that a community could use their own cost data or manufacturer, or even their own weighting to figure out what might work in their situation. Okay. So here's an example of what our transect data look like. At the bottom plot, you have your measured transect. So this is a cross section of the river, just to orient yourself. If you're looking downstream, right bank is to the northwest on your right, and then left bank is towards the southeast. So town is on the right bank here, and flow is going into the page, so towards the southwest. So this is at Crooked Creek. And one other interesting thing I wanted to point out here, it's just, this is one of the towns where the channel is on the same side as town. And when I get into later about the cabling distances, that's important. It's going to bring their costs down a lot. So, and what this shows, so you have on the lower plot, you have flow speed in meters per second against the depth of the transect, and the same on the upper plot. And this shows that the measured transect matches very well with our model transect, which means that we were happy with how we had tuned our HEC-RAS model for the future models. And the other thing that's interesting in this plot is you can see the center channel has 2 meters a second velocity, and it's not exactly in the deepest part of the channel, which is called the Thalweg. And I'm bringing this up because we need to recognize that these braided riverbeds do migrate. The channels don't always stay the same. And so it's likely that the location of the current energy converter might change from year to year slightly as the channel is adjusted. Okay. This is a flow duration curve. So on your y-axis, you're seeing discharge in meters cubed per second. And on the x-axis along the bottom, you're seeing percent exceedance. So what that's saying, using Stony River as an example, is 100% of the time, and this is using the 20-year data set, the discharge at Crooked Creek is always a minimum of 1,000 meters cubed per second, whereas only about 95% of the time, at Stony River, does the flow exceed 2,000 meters cubed per second at this location. And in general, the pattern that you can see is that the higher discharge is found downstream, and the lower discharge is found upstream for the most part. And unfortunately, a couple of the HOBO pressure sensors went missing, or the data was corrupt. And so we weren't able to do all of our hydrokinetic resource calculations at the communities of Sleet Mute and Calskeg, so they're not included in that. This is what the time series of velocity, modeled velocity and instantaneous power look like. So on the red line is modeled velocity in meters per second, and the blue line is instantaneous power in kilowatts. And this is over the open water season from June 1st to mid-October at 2 sites, for example, at Crooked Creek and Antioch. And what we did with this instantaneous power was we summed it over the entire open water season to obtain the total hydrokinetic resource. And once we have the total hydrokinetic resource, we can start looking at community energy demand and comparing and figuring out, how many current energy converters would be needed at each location. So what you're looking at here, the gray bars are the monthly mean plus standard error, standard deviation bars of diesel energy used for the 5 years prior to this to the present. So this is energy demand in megawatt hours for the 4 months during the open water season, and that's at Crooked Creek and at Antioch. And I also wanted to point out the y-axis, the scales are on completely, they're order of magnitude different. So Crooked Creek, it only goes up to 35 megawatt hours, but Antioch, it's a much larger community. And so the scale bar goes up to 300 megawatt hours. And what this shows is that one current energy converter at Crooked Creek is able to meet 72% of the demand during the summer months. And since our goal was to try and meet 100% of the energy demand at each community, at this site, we recommended 2 current energy converters, which would produce 145% of the current demand. Antioch, which is a larger community, we found that 1 current energy converter, or KEC, would only meet about 6% of the community's demand. So in order to meet 100%, or actually 98% was the closest we could get of the community demand, at this site, we would recommend an array of current energy converters where you would have 4 different moorings with 4 current energy converters on each of them for a total of 16 current energy converters. So that's what we did at each site to figure out the number of current energy converters required. And then once we knew how many were required, we could start looking at costs. So to calculate the levelized cost of energy, we use the National Renewable Energy Laboratory online tool. The website is here. It's really easy to use. And we spend quite a bit of time looking at the different costs. So let me change. Oops. I'm having a hard time. I lost my mouse. Okay. So looking at the capital costs on the upper left, whoops, these first section of capital costs, so that are associated with manufacturing, those came directly out of the Pervisi EPRI report from 2008. And then we converted it to current currency. And then the next part of the capital costs, the debris diverter, the on-site assembly, those costs we got from our experiences at the Tanana River test site that's operated by UAF. And I wanted to point out that our capital costs did include the cost of a debris diverter, which I believe, I'm not going to go into great detail because Ben should have some slides explaining that in his next talk. And then I contacted many different manufacturers to get quotes for shipping and airfare and the various underwater and underground cabling and the connection costs that go into microgrid connection. So all of those together combined into your CapEx, and then which is a one-time upfront cost. And then on the other side of the equation here, you have your annual operation and maintenance costs, and those include things like airfare, flying somebody out each year. We're assuming that we're going to have some local hire as well, but that at least one person would go out every year from the company or from the university to assist with the deploying and the retrieving the device each at the beginning and the end of each season. And then, of course, there's always going to be maintenance and repairs. So any kind of replacement parts and repairs were included in your annual operation and maintenance costs. So together, the CapEx and the OpEx are combined. They're calculated over 15-year expected lifetime current energy converter. And the other thing that I want to point out is this capacity factor. So that is a ratio of the extracted power, like what you can actually get out of the device, divided over the rated power. So what the manufacturer says the device is capable of producing. In this case, our capacity factor was 26%. And that includes your 38% availability, because the open water season, you're only able to get energy in this floating technology that we're suggesting during the 4.5 months of the open water season. So that's where that 38% availability comes in. And the end result is that you get LCOE, so levelized cost of energy, in dollars per kilowatt hour. Okay, let me go back to my laser pointer. Okay, so we have looked at the LCOE and the hydrokinetic resource, and we've looked at the community energy demand. So now I'm going to explain some of the other factors. And if you recall, let me go back a slide. If you recall, the factors were weighted by importance. So they're weighted with a 1, 2, and a 3. And then within factors, we also ranked them from high to lowest, where a score of 1 is the least suitable and a score of 5 is the most suitable. So I just wanted to point out a couple examples. For the LCOE, a site where the cost is low, so less than 30 cents per kilowatt hour, where we're saying would be a suitable location. And a place where fuel is high, so greater than 50 cents, is also suitable, because if you think about it, if the fuel cost is already cheap, then it doesn't make sense to replace it with LCOE of renewable that's the same or more expensive. I think I have an animation here. There it is. I also wanted to highlight for the sensitive environmental considerations, we looked at locations where there's fish spawning or rearing habitat or wetlands, and anywhere where there was fish habitat was considered least suitable, and combined fish and wetland got the lowest score, whereas if there are no sensitive environments, then they got the highest score. And we used data from ADF&G and US Fish and Wildlife Service to obtain that environmental data. The next factor that I want to talk to you about is this climate change risk. So the Alaska Division of Geological and Geophysical Surveys came up with a report where they ranked Alaska's environmentally threatened communities from lowest to highest. And we adopted the same scoring. And this idea of USTEC, it comes from a combination of erosion, flooding, and permafrost degradation. And we use it as kind of a measure of the community's resilience, where if there's going to be permafrost collapse and flooding and USTEC will take place, then the community would score low. Whereas if there is little risk of that happening, then the community would score a 3. So that was a climate change factor that we included. Let's see, some of the other factors, the annual statistics from the Alaska Energy Authority power cost equalization program were used for population and to look at avoided fuel costs. So you can download PCE reports for each community, and it shows both the residential rates charged and also the fuel cost per kilowatt hour. And we selected fuel cost per kilowatt hour as our measure to compare to our LCOE instead of the residential rate charged. And that's because there is a significant amount of subsidies. And so if a manufacturer were to think that the rates were 58 cents per kilowatt hour without considering subsidies, then it's just something they need to take in consideration. So the avoided fuel cost was something that we would definitely be replacing with renewable power. So that's why we chose that measure. Another factor we looked at was the distance to distribution lines. So we looked at satellite imagery and community plans to measure the distance from the edge of the riverbank to where we determined was the best location for a current energy converter to the closest 3-volt distribution line or power plant, whichever was closest. And I want to make a point that our assumption was that this would be a utility cost to extend the overhead lines to wherever our shore station was. And that's why distance to distribution lines was considered as an independent factor. It wasn't included with the cost, with the individual power producer costs that we did include in our LCOE. And so for here, I'm using Antioch as an example. This is one of the sites where the closest power pole is only 30 meters from the riverbank. So the cost would be low for the utility to extend because there is no extension required here. I also wanted to show here that the underwater cable was measured on the underwater cable distance was measured. And the reason I'm bringing this up, even though it's not part of it's a separate factor that's included in the LCOE, is that these cable costs, that both the distribution lines and then the underwater cable costs ended up being fairly significant. And I think that contributed to how our results weighted out. And so the LCOE included both the cost of the underwater cable, which is calculated per meter, and also the microgrid connection. And we did not distinguish for all of our sites. We just said across the board, we're going to take 30 meters. That's going to be a combination of armored cable and buried underground cable in a trench. And so this site essentially has 0 distance because that 30 meters to the closest pole is incorporated into our microgrid connection costs. Okay. So if you remember our site suitability scoring, we take our factor weights weighted by importance from most important to least important. So the weights could be 1, 2, or 3. And then we took our factor ranks from least to most suitable. So in this, for the ranks, you could get a 1 to 4, and then we multiplied the factor weights by the ranks to get our final score. The total possible score was 72, and the lowest possible score was 18. And our final scores all ranged between about 40 and 50. Our LCOE ranged from about 30 to 50 cents per kilowatt hour. And then here we have the number of current energy converters that we recommend. For most of the smaller communities with a lower energy demand, we recommended 1 or 2. And then for the larger communities at Antioch and Calskag, we recommended a raise of multiple current energy converters. And I just want to point out on the slide, Sleepmute and Calskag have the missing hydrokinetic data. So take those 2 sites with a grain of salt. We are suggesting that Sleepmute might use 2 current energy converters, and that was purely based on the demand of the community since we don't have the hydro data. I wanted to still include an LCOE and look at the costs and the distances for the site, but we don't have a final score for it. And same with Calskag. Calskag has about half the energy demand as Antioch, and that's why we were recommended about half the number of current energy converters, but more data is needed to answer that for sure. So to see those results in a map form, Antioch ended up being the site that was most suitable for river energy conversion, and Stony River was the least suitable. And what is interesting about the pattern here is that the further downstream the communities are tends to be more suitable according to our analysis. And again, Stony River and Calskag don't have any data, so they're not included here. So so this is interesting that they're the downstream communities that are more suitable, and I wanted to look at some of the data, like what is the causing this? And so I'm just want to throw up a couple of figures to conclude with to show what some of the patterns are. And I think from the figure to the left, so this is the cost per kilowatt hour, the LCOE. So the green bars are showing our LCOE for each community, and then the gray background is showing the fuel costs per kilowatt hour. And in general, what you're seeing is that the cost for river energy conversion is on par with what they're already spending on fuel. There's a couple communities like Strathclyde where the resource was really high and the fuel cost was low. But okay, so that's that figure on the left. And then on the right, this I thought was pretty interesting. The CapEx on the x-axis is the initial investment in funds. So it's, up to $3.5 million. That's what your green bars are at Antioch, and about 2 million at Calskag to put in a giant array of these current energy converters. And then down here, the other communities where the demand is lower, you can see that the capital investment is larger if you have 2 current energy converters versus the smaller communities only have 1. So, and then I think the other point I wanted to make on this figure was that although the initial investment was high, the installed cost, so the cost per kilowatt hour is reduced by by the increased number of current energy converters. Okay, look like I'm almost out of time. So I put this figure in to talk about the differences between the distance of distribution lines. So Stony River, even though it has quite a high resource, you can see that it's almost 1,000 meters to the nearest power pole, and that could have been part of the reason why it weighted low in our results. And I wanted to show this example of community energy and demand and population to show Antioch has a much higher demand than anybody else. But it's interesting that the populations are the same between Antioch and Calskag, but the demand is much higher in Antioch. Calskag is actually two communities that are intertied together, Lower and Upper Calskag. So that was an interesting result there. So in conclusion, we presented a methodology to evaluate site suitability. We applied it to Kuskokwim River. I think the LCOE results compared to avoided fuel costs show that current energy conversion is a potentially viable option at these communities. And what is the main take-home message about our method here is that it can be adjusted to suit your own needs. So you could change the weighting or the ranking of these factors if you felt like we missed something or something was more important, and you could put in your own cost data into the LCOE and back out how to determine if your site is going to work or not. A couple of things for future work we're looking at, some more targeted field data now that we've had a really detailed look at where the channels are and relative to where the power infrastructure are. There's a few sites where we'd like to go back and do some more targeted field data. And we've also been in discussions with ORPC about looking at some winter ice and under ice flow measurements to try and get at that winter season. And I want to thank all the people who have assisted me and our funding. And the citation for this work is, it's a manuscript that's in preparation for submission. Thank you, and I'm happy to answer questions.
Thank you so much, Eloise. That's some fascinating work. Yeah, this is going to lead to some really excellent developments, I hope, in the future. So let's move on to the next speaker. We've got a lot of great questions, and we're gonna come back to those. So next we have Ben, or Jeremy. Are you presenting this, or is it going to be Ben?
I'm here.
Oh, okay, Ben is here. Okay, good. Okay, Ben Loeffler, he is also a manager at the Pacific Marine Energy Center and works at ACEP at UAF. He's a research professional in hydrokinetic research group, and he's also University of Alaska Fairbanks research manager for PMEC. He's a professional mechanical engineer in the state of Alaska, and his primary efforts right now include engineering and project management for research projects and operations at the Tanana River Test Site in Nenana. So take it away, Ben.
All right, thanks, Shana. Yeah, so like we said in the intro, I actually get to work hands-on with the design and building and testing of devices that we tested our test site in Nenana. And go and get my pointer going. So in this presentation, I'll touch briefly on sort of what our focus is as a university and what our motivations are for hydrokinetic research as it pertains to Alaska, and what the motivations and challenges are there, and the kind of work and a little bit of an overview of our test site on the Tanana River. And then I'll talk about two of our recent projects that are sort of perhaps outliers in the sort of field of technologies that are being developed. And then at the very end, I'll sort of give a list of other technologies that interested folks might want to look into. So motivation. So at ACEP, our motivation really is to just try and advance hydrokinetic energy to the point where it's valuable to Alaskans, and it can provide power to Alaskan communities. And some of the challenges that arise are that these devices are generally small scale, which means their cost per kilowatt tends to be higher. A lot of the commercially developed systems are rated at say 3 meters per second, like Levi was saying, but we don't really have rivers that are 3 meters per second. And because it's a cubic relationship, you may only get 30% of the output of the device on an actual river. And then within the technology itself, efficiency is problematic. There's a torque speed trade-off. So as your device gets bigger, you get more torque out of the river, but your speed goes down because you're limited by the speed the tips of the rotor blades can turn. But your generators all need to be 1800 RPM, or off-the-shelf generators that are low cost want to spin at 1800 RPM. And so how do you couple a 100 RPM turbine to an 1800 RPM generator? And then reliability, Levi talked about sediment in the Cook Inlet. There's also sediment in some of our rivers, certainly in the Tanana River. And then debris here, a picture on the right is a turbine at our test site that snagged a log that was floating down the river. Environmental impacts, that's more in the realm of the fisheries folks, but that is a challenge. And then of course the integration. So the last two I won't talk about at all. So a little overview of our test site on the Tanana River in Nenana. It's about 55 miles southwest of Fairbanks along the Parks Highway. So it's pretty accessible, easy to get equipment in and out. We have open water May to October. The velocity has quite a large range on this stretch of the river. So in the fall, if it hasn't been raining, we'll get down to 1.2, 1.3 meters per second. If we have high water, lots of rain and sun on the mountains and the glaciers in June or July, we might get up to 3 meters per second. But generally, we think of it as a 1.8 to 2 meter per second resource, which is kind of consistent with what Eloise was showing for the Kuskokwim and similar for the Yukon as well. Can expect a depth of 6 meters, but obviously it changes with the river level and with the channel movements. And so, 10 meters is certainly present in some places. And this stretch of river is fully permitted, and we keep those permits current year to year. And so it's pretty easy to get technology into the water on a fairly short timeline. There's no onerous permitting to speak of. So on the water, this is our on the water infrastructure. So on the right is our research debris diversion platform, and we're hoping to get an updated version of this into the water this summer, so a completely new debris diverter design. And what that does is it deflects major surface debris and provides sort of a sheltered area downstream for our research barge, which is roughly 20 by 40 foot floating platform, aluminum pontoon boat. It's covered up in this photo, but there's a moon pool in the sort of the middle downstream end of the boat where systems can be deployed between the pontoons, or in this system we're testing. In this case, we're testing the water horse off the transom of the barge. And then downstream here is the inclined plane fish trap, and so this drops a net into the water column roughly the same depth as the device being tested, and allows us to sample fish downstream of the turbine. And we can either we always have them in the water when we're running, so we can see what sort of arrives naturally, or the fisheries folks will go catch margin species, and we'll insert them into the water upstream of the turbine and then try and catch them, recover them on the downstream side. And then just without comment, here's sort of a photo of the type of floating debris that a system might encounter if it's not protected by a debris diverter. This would be typical of this river or the Yukon or the Kuskokwim. And so now we'll get into two particular systems that are kind of in the R&D phases that we've been working on here at ACEP. So this first one is called the Water Horse, and it is a galloping current energy system. So rather than rotating a turbine due to lift or drag on an airfoil, this system oscillates up and down, and I'll play a video. But these weird aluminum shapes on the left here are called bluff bodies, and the flat face that's down on the deck is actually inserted perpendicular to the flow. So the river flows flowing directly into the flat face, and then vortices trip over the upper and lower edges of this and create an alternating lift. And so this system is based on intellectual property from Renergy Incorporated. And we tested, this is the first version we tested in 2020, and then we tested an updated system this past summer, 2021. And so the thinking with this approach is that These type of systems are expected to be very low efficiency compared to a turbine. But if they're a lot cheaper and more robust, that LCOE, that levelized cost of energy that Elle talked about, could be competitive. So if you're half as efficient, but you're also half as expensive, you're the same cost per kilowatt hour. And so here's some background, just sort of an image of the vortex shedding. And so this is a flow visualization for a circular bluff body, and Renergy found that flat face sort of accentuated the vortex shedding effect. But essentially, as the velocity increases, these vortices, so the blue are vortices tripping off the top and the red are tripping off the bottom. And you see how basically these 4 panels are increasing velocity. And you just get sort of more complicated vortex streets or vortex patterns that generate an alternating lift force. And so similar to how an airfoil works, but due to pressure differentials from the vortex. And so sort of the scientific analysis, it's the shedding changes with the Reynolds number, which is proportional to basically the velocity and to the diameter of the bluff body. So you can scale your diameter to your anticipated velocity to arrive at the Reynolds number that you want. And then the shedding frequency is described by the Struhel number, where again, the frequency is proportional or inversely proportional to the diameter L, and this ratio over the velocity tends to be about 0.2. And so what you do is you design your oscillator system so that it's like a mass spring damper, and so the mass and the spring stiffness and the damping from your generator are sort of matched to the vortex shedding frequency. And some of the best research that's been published has been on the Vivace device out of the University of Michigan, so you can look that up. They've published probably dozens of papers, and they've got YouTube videos, and they've, I think, done a couple pilot deployments of a bottom mount system in some rivers in Michigan. So here I'm going to play a video of our floating platform deployed system. And I guess one big thing to note after you sort of take in how the device is moving is to look at how the barge is moving as well. And I'll talk about that afterwards. So this vertical beam here is the support. The bluff body is roughly 3 to 6 feet underwater. There's a chain connected through here that ultimately compresses this spring pack and also connects to a power takeoff system that spins the generator. And so this was our version 1 device. And big takeaways from that. The data collected that summer were, here's the electrical power output. So this top one, we were implementing a Sprague clutch to mechanically rectify the generator rotation. And so the power obviously comes in these pulses with each stroke of the oscillator. And then we actually removed the mechanical rectifier, the Sprague clutch, and used an electrical rectifier instead. And so we were able to double the number of pulses and improve our efficiency. And so over here on the right is velocity on the x-axis. So on the days we were testing, we were between 1.8 and 2 meters per second. And our water-to-wire efficiency, so the power, the energy present, or the power present in the water, like what Levi had talked about in kilowatts per square meter, compared to the electrical power that actually came out the other side. Our electrical output was anywhere from under 1% to almost 3% of the power that was available in the water. So very low efficiency. A good turbine will get you up into the 40 to 50% range would be a very high performance turbine. So obviously quite low, and we're clearly not 1/30th the cost of a turbine, and so this was not going to be a competitive efficiency. And so out of that, our year 2 device, we implemented a power signal conditioning system with off-the-shelf components, essentially rectifiers, and then a DC charge controller to provide a constant output voltage to charge a battery bank, which then could run an inverter to the grid. there's a lot of instrumentation cables going everywhere for all the data collection of power, current and voltage at all different stages. And I don't have good imagery or video of our testing this summer that I was able to pull in, but we saw significantly improved efficiency at much lower velocities. So we were testing between 1.2 and 1.8. Down here, these squares and triangles are sort of the representative efficiencies from 2020 or 2021. And this is not fully processed data, but these are moving average data points. And so we were operating sort of in the range of 6 to 8% efficiency. So, you know, perhaps a 2 to 4 fold improvement in efficiency. And so that's the kind of thing we're trying to achieve at the university level, is sort of this, you know, learning about the details of the technology and trying to make incremental improvements. So the second device, or the second project, and this one is ongoing currently. It just started this past July, and we ran quickly to get a device in the water in September. And so this is the Sharks program run by ARPA-E, which is Department of Energy's Advanced Research. I forget the exact acronym, but their mission is to advance high potential, high impact energy technologies that are too early for private sector investment. And we partnered on this project with a startup company, Blade Runner, because we thought they had a really interesting design that could be really well suited for Alaska. The Sharks program focused on co-design. So instead of sequentially designing your system from one end to the other, thinking about all parts of your system holistically and designing them together. And then controls co-design. So what can you do with controls to sort of lessen the cost of other aspects of your mechanical design? Suitable for tidal and river. It's a current energy converter. And Sharks focused on what they called a metric space, which is sort of a way of normalizing the LCOE into some constituent parts. And so they evaluated the technologies based on their water to wire efficiency, which they called M1, their structural efficiency. So how much material cost is there per swept area of rotor? So if you multiply M1 times M2, now you have the cost per kilowatt hour produced for a given resource, and then the operating expense. So how much O&M operating maintenance costs are layered on top of that add to your LCOE. So here's a sort of a not to scale schematic of the Blade Runner system. They've got a generator and a floating housing, and this housing is supported by a single mooring line, either to an anchor or some other fixed point. And then they have a flexible torsional cable, so this synthetic cable that is torsionally stiff but can bend and allow the rotor to sort of move about in the water column. And then the rotor itself is designed to be debris resilient. So this is an old rotor, but they kind of use biomimicry to create curves and shapes that are less prone to snagging on debris. And so the big thing here was actually that M2 metric. So this system, everything is in tension. There's no cantilevered loads, so there's no need for big, strong steel members. The mooring line comes into a simple steel frame in the generator housing, and then there's a thrust bearing that carries the load from the torsional cable that's in tension, and then the drag on the rotor sort of keeps everything pulled straight. And so these are designed to be modular, roughly 2.5 kilowatt output for a 2 meter per second river. And because that single pole mooring, we're going to explore deploying them from the shore without any boats, basically using a boom arm to swing it out into the current. So as I said, we sort of sprinted to get an initial prototype into the water. So on the left here is their rotor hub, and they're installing one of their blades. In the middle is that floating generator housing, and we've got an inline torque sensor and a gearbox. Excuse me. And I should say this is a permanent magnet machine, but another component of this project is we've partnered with a startup company called C-Motive Technologies, and they have an electrostatic generator that should be highly efficient at 100, 200 RPM speed range. So like I mentioned at the beginning, that electrostatic generator offers the potential to directly couple a 100 or 200 RPM large diameter rotor directly to a generator that's highly efficient. But unlike the water horse, this system is pretty benign. This block on the right is going to show a video of it operating The generator housing is floating in the water. And we've got a buoy off the tail end of the rotor. So the rotor is fully submerged. Buoy rotating. The system is at work producing power. And again, with the fishing barge downstream sampling for fish. So like I said, this is an ongoing project. We have 2 more summers of field testing with iterative design development. But this first year of testing produced roughly 30% efficiency, 28%, I think, water to wire. And that was allowed them to validate their computational fluid dynamic modeling. So they're obviously using advanced computer software to design their blade geometries. So here's some pretty pictures from Blade Runner, and they're working with a company called Moshman Research to develop their blade shapes. So they're looking at blade-to-blade interactions and detailed shape morphing to optimize their rotor performance. And so, like I said, this summer we'll do our first shore-based test deployment with a single modular unit, and hopefully do an array deployment from the shore next summer. And we're also doing some testing of that torsional cable, because we're operating at torque levels that have not been operated at with a free end that's not fixed. And so we have to balance that drag force with the torque to prevent the cable from kinking. And this is my last slide. So this is just a wet people's whistle. I'm not an encyclopedia of current energy converter technologies out there, but some things to look into if you're interested in learning more. There have been some successful pilot sites in the United States. So you'll hear more about the ORPC roughly 40 kilowatt scale system in Idiagig. Verdant Power also has a roughly 100 kilowatt scale system in the East River in New York. There are smaller scale commercial offerings, a few that came to mind readily when I was making the slide. So New Energy is the system that went in Ruby and Eagle. And in that first picture, these vertical axis cross flows seem to be prone to debris accumulation, but you could have a site where debris is not a problem, where that might be suitable. Smart Hydro has an interesting axial flow system that has a floating platform and has a debris screen. And I've seen similar systems on like the Rhine River in Germany being tested. And then also in the US, Hydro Energy seems to be having some success putting hydrokinetic systems in hydroelectric dam spillways and recovering energy from the flow of water out the spillway. And then there are a number of development and testing locations, none of them river. We're really the only show on river testing, but a lot of systems have gone in at EMAC, the European Marine Energy Center in Scotland, including very recently a 2 megawatt orbital marine system. And I think Orbital is going to be talking in this workshop. Number of systems have been tested or attempted at the Bay of Fundy, off Nova Scotia, and you can look into the UNH Living Bridge, and there's also a lot of research going on around the Florida Gulf Stream, so you could look into that as well. And then a couple acknowledgements. The Water Horse is funded by Department of Energy, Water Power Technology Office, and there's the award number. And SHARTS is being funded by Advanced Research Projects Agency, ARPA-E, Department of Energy, and that award number there. And that's it. I guess Shanna will handle all the questions. Thanks.
Thanks so much, Ben. Great to get some of the details about what's been going on up there. Okay, we have about 11 minutes here for questions now, and we have quite a list of questions that have come in from the audience members. Some are to specific panelists and some are to the group. So I think I'll start out with some that are maybe a little broader. So to all the panelists, Eloise cited some pretty high costs, and there was some questions around whether or not there are funding opportunities that might offset these costs, either from state or federal grants, or if there are ways that maybe communities could collaborate on construction costs instead of having bearing the burden of those costs individually. Does anyone have any thoughts on that?
I would just say that the cost would absolutely come down if communities shared, because you're just barging all this stuff upriver. And if we did our analysis for each individual community by itself. But a lot of the cable and the materials, you know, the more, if you buy it in bulk, the price goes down. So it would absolutely bring the cost down, sharing like this. I'm gonna let someone else make suggestions on where to go for funding though.
Any ideas? No. maybe we'll hear some more in the future. But that is really interesting to think about in terms of the communities collaborating on, you know, possibly going forward with some of these developments. Another question related to that is what kind of capacity would a community need to be able to do the seasonal haul out and replacement? And do the communities have that kind of capacity? That's
well,
great.
for the floating pontoon that we're recommending, which is similar to what Ben was talking about at the Tanana Resource, the Tanana River test site. Any local small boat should be able to pull something out there. So we generally, Ben can speak more to this, but we'll take 2 boats for safety. So a couple operators for each boat and to pull a barge out. So you need a loader to bring a heavy mooring down, and then you need to deploy that one day. And then the next day you just need a boat to go out and connect your barge to the mooring line. So that was why part of the reason we went with the floating pontoon style, to make it easy for what people would already have in these communities. And if you have anything to add to that, Ben.
Yeah, I would second that the floating system makes sense for a lot of reasons, and that yeah, once you have the mooring, I think you would need to, you know, get a barge company to install that the first time. But then after that, you can recover the mooring lines seasonally with any motorboat. And our barge, we've deployed it from sort of an minimally improved gravel ramp into the riverbank on rollers, and just pushed it in with a bulldozer or, you know, a front end loader, and then lashed a motorboat to the transom and driven it upriver and gotten it on the mooring line. So it can be pretty low tech and still functional. It just requires time and coordination and a little bit of expertise.
Excellent, thank you both. Just, I guess, continuing on with the questions of cost. This question was maybe more for Levi, but if anybody has any answers. Do you have any sense of the estimated costs to upgrade the rail belt transmission capacity to accommodate more tidal energy capacity?
No. I'm going to take a pass on that one. That's well outside of my expertise area. I just saw Curtis Thayer pop up. He might have better information on that than me.
Yeah, just to let you kind of know where we are with that. The railboat utilities are looking at increasing the line out of Bradley into Anchorage. The upgrade cost on the lines alone, we're figuring about $200 to $300 million. We're also looking at battery in Homer, another one in Anchorage, whether that be part of the project or not. But we're actually a little closer to reality on that. To give a little background, when the Bradley bonds were paid off this last summer, that allows for about $12.5 million. That was what we call now excess payments. We can use that for debt service for required project work as it's deemed by Department of Law. And so we're going through that process through the Department of Law, but we anticipate that we're going to be able to bond about $200 to $250 million worth of work and do that bonding this year and start the upgrades later this year into next year. But that's actually upgrading, like I said, from Bradley Junction all the way up through Anchorage. So it is something that we're currently doing underway. So we're taking it from 115 to a 230 line. So we'll have plenty of capacity.
Excellent. Thanks for that answer, Curtis. That's great to hear. So here's a question for Eloise about your study. So when you were weighting the importance of the different factors in the model, how did you get community input on that?
Let me just pull up that's a really great question. That's something I've been thinking a lot about. I think that community input is really, really important. And we did not get enough community input, and we could definitely use more. When our student did her project, she weighted the hydrokinetic resource as the most important. And when we, started looking at it and thinking about it some more, we kind of realized that it really doesn't matter how amazing the resource is. If it costs $20 million, no one can afford to invest in it, then you're not going to get renewable power. So we looked at our economic factors and we weighted them most important because we're trying to be realistic. And I think what you're getting at about community input, that's what we are saying. This is just an example for a tool you can use, and you can adjust it and put your own factors in. We've been talking about going out and getting some winter ice measurements, and I would love to get some community observers to help us get ice thickness measurements in the winter and have a discussion with local communities and tribal leaders. I've been reaching out to some community outreach coordinators to start that conversation. I think that's really where this needs to go now. And that's part of the reason for having this workshop. We were hoping to springboard that conversation. And please email me if you have any thoughts. If you're in a community and you have ideas, I want to hear from you.
Excellent. Yeah, thank you. And it sounds like the model is something that can be adapted for different communities then, like with their own inputs. Okay, excellent. Well, we only have we have 3 more minutes, but I want to ask a question to the whole panel here. If there are developers that are watching this now and are interested in getting involved in commercial development or moving towards that in Alaska, how can they do that?
My opinion on this is, like I said, I think these technologies are still relatively early stage. And so finding ways to demonstrate in the US markets that your technology is reliable and then sort of starting to share your cost data. Those are the 2 entry points. Those are the main sort of hurdles, in my opinion, that need to be overcome. Because when we talk to communities, they want reliable power. They want systems that they know are going to work. And if they're going to make a big dollar investment like this, they need to know that it's going to be reliable. And the same goes for larger scale deployments in Cook Inlet. If the state or utilities or however you would pay for larger scale projects, I think you've got to demonstrate that the technology is reliable, and I just don't think we're quite there yet.
Yeah,
I think we're close.
Yeah, I mean, I would make the obvious sales pitch for our test site as an opportunity to demonstrate that reliability and to have sort of a third party validate that data. And ACEP also can provide a lot of value on the integration side with connections in local remote utilities and understanding of their particular microgrids. So that would be my advice: is come talk to us.
Excellent. Thank you so much. Round of applause for our panelists. We're at time here, but we'll hopefully see you back at the next panel here. And thank you so much. Wonderful engagement.
Thanks, everybody.
Great. Thank you very much, everybody. I'm learning how challenging it is to keep track of the chat and everything else that's going on at the same time. So definitely appreciate all the moderators that I've seen handle this with grace and ease. So great, and thank you very much, Shana, and thank you to Ben and Levi and Elle for those great presentations. So now we're heading into a 15-minute break. During that break, we'll be showcasing some of the upcoming events that are part of this series, including the Arctic X event that's being put on by the Arctic Energy Office, the DOE Arctic Energy Office, and the DOE Office of Technology Transitions. And that is happening in person on May 23rd in Anchorage. Following right along after that is the Alaska Sustainable Energy Conference. And again, that's that same week right after Arctic X. And again, that is the intent there is for that to be in person. During the break, we have a short video on research being done by UAF and our partners at Pacific Northwest National Lab. This is a video I mentioned earlier, but it'll get into a little bit of our work on interaction of fish with these turbines. So stick around to learn more, and we'll see you back here at 10:30 Alaska time. So we'll have about a 15-minute break.
Hydrokinetic turbines are devices you put in the water that typically spin, and the spinning motion produces electricity, but that also creates a risk of collision with fishes.
I look at a variety of stressors, but my specialty is probably collision risk, which is the risk that animals have of interacting with some of these marine energy devices.
We're gonna go downstream first.
Okay.
And we are specifically trying to characterize the fish community that may interact with the turbine while it's in the water.
Yeah. 6 chums.
So we care about all fishes, but some fish are used by humans more than others, and so salmon are the main species of interest. And so in a river like the Tanana, we have 3 species of salmon: king salmon, chum salmon, and coho salmon. This river here, that can include long-nosed suckers, lake chubs, a variety of whitefish species, burbot, which are also recreationally important, and pike as well. And there's always a risk when you put something spinning in a river that it will have some sort of interaction with fishes. And so we're trying to understand what risk a turbine may put fishes at.
Tanana River Test Site here in Nenana. And we've been doing a lot of work on characterizing debris, hydrodynamics, so river velocity, and then we've also been doing a lot of testing of infrastructure, new turbine architectures, new ways to capture the energy in the moving water.
What PNNL people are doing is trying to see if they can visualize or see king salmon smolts, which are about 8 to 10 centimeters long, swimming down to the ocean with this acoustic camera. And then the way to ground truth or verify what they're seeing is by fishing behind their equipment or the beam of their equipment. And so that's another purpose for the fishing equipment that we use.
Oh, there's a burbot in there. And a little king.
Wow.
So these collaborations are really important because UAF, for instance, has a specialty with a specific test site here, fisheries, specific to Alaska. And PNNL, I'm coming with specific expertise based on sensors such as acoustic cameras. Instead of keeping those expertise separate, we're able to put those together. Additionally, there's a large push across the country to combine expertise with national laboratories and universities, essentially our iconic research institutions coming together.
Partnerships are important because hydrokinetics, it's an inherently interdisciplinary science. And so to have the expertise to cover all the aspects of it, you really need those kind of cross-disciplinary partnerships. It's really hard to get all those pieces together.
The benefits of this collaboration and the research associated with, you could start at a very high level and discuss the benefits to the country as a whole. Renewable energy developments to increase and diversify the portfolio of energy that we depend on. I'm standing here on the banks of the Tanana River near the small town of Nenana, and there's advantages there. Everything from the power development that potentially could be used here or similar development at other villages or other small towns, as well as jobs that could be developed from this locally, as well as bringing in jobs from outside.
My name is Tim McManus. I'm the first chief, and it's a volunteer position. Got about 200 people live here. Our school, you know, we got the kids. We've got a boarding school that kids come from other villages and stay here. So I'm very excited about UAF and the collaboration with the Native Council on this project. People have been asking me, what's that thing out in the river, Timmy? Who's fishing? To be able to learn about it and figure out what was going on was a big help.
We've been doing research in the Tanana River test site since 2010. As we build this knowledge base, it allows us to not start from scratch, and we can advance the field of clean energy in rivers.
Welcome back, everybody. We hope you enjoyed this morning's program and the break. And now we're pretty excited to dive into panel 2. This panel will feature developers of current energy converters from the US and Scotland and provide a sense of just how advanced these technologies have become in the last few years. A lot of good conversation this morning after the first panel, and I think you'll find in the next 2 panels, especially the questions with regards to communities and how to get things done in the communities, and then also community input. Those are appropriate, very appropriate questions for these panelists as well. So please keep those questions coming. As a reminder, during the session, questions can be submitted via the chat and will be addressed by the panelists in the Q&A session. So with that, it's my pleasure to introduce you to our moderator, David Lockard. He's the infrastructure engineer with the Alaska Energy Authority. So David, take it away.
Thank you, Jeremy. I very much enjoyed the presentations this morning. Can you hear me okay? I'm guessing you can. So I wanted to start out by thanking Curtis Thayer for his introduction of my agency earlier. He did a great job of that. There are a number of aspects of the things we do that were mentioned and that are relevant to this effort to develop hydrokinetics for Alaska. I just wanted to emphasize a few of them. We have a considerable history integrating run-of-river hydro projects into small rural diesel powerhouses. In some cases at close to 100% penetration, in some cases much less. For example, the Tazimina River Hydro near Iliamna and the Gartina Creek Hydro in near Hoona are both kind of success stories of the Alaska Energy Authority, and that's, I think, relevant to our discussions today. Curtis mentioned plans for new transmission. You can find a 2017 transmission plan on our website in the library, and one of the things it includes is a high voltage direct current line across Cook Inlet. Now, this is not funded at this time, but it is proposed in that plan. Might be interesting, particularly since we heard earlier that there's more power, tidal power on the west side of Cook Inlet. I wanted also to mention that in addition to what you can find on our website, there is more power cost equalization data available directly from AEA. We've got monthly data. It includes things like peak demand and other aspects of the power use in the villages that might be interesting to people who are doing the analysis. And finally, I wanted to mention, it was great to hear Melanie Wilson's name earlier. She was a neighbor of mine, and I remember running into her, walking our dogs in the park, and having great discussions about hydrokinetics. So with that, I'd like to get into our presentations today. Our first speaker is Marek Jakinski, the Director of Development at Ocean Renewable Power Corporation. As ORPC's Director of Development for Alaska and a lifelong Alaskan, Marek works with local regulators, communities, and electrical providers to develop tidal and river-based energy projects for ORPC. Having grown up fishing in the Gulf of Alaska, Merrick brings his familiarity with the traditional way of life to the technical and logistical aspects of project development through his background in contract negotiation, construction management, and engineering design. Merrick?
Thanks for that introduction. Let me get my screen pulled up here. The bar on top is coming over my thing. There we go. All right. Well, thanks, guys. So my name is Merrick Chikinski. I'm with Ocean Renewable Power Company, as previously mentioned, and I'm going to be speaking about our active project here in Alaska, which is our RivGen installation in Igiugig, Alaska. Really quickly, I'll give a background about what ORPC, or who our ORPC is, what our river hydrokinetic device is all about, and then I'll go further into the project here in Igiugig, Alaska. So quickly about ORPC, I've been in business since about 2004. We have 37 employees currently situated around the world. Our main office is in Portland, Maine. And we also have an office in Montreal, Canada, and Dublin, Ireland, as well as a few of us here in Anchorage, Alaska. And recently we've added some subsidiaries in Chile as well, which has been an interesting development there. ORPC is focused on creating power from moving water. Our devices use a cross-flow turbine, which you can kind of see in my background in my picture here, and we'll get more into that a little bit later, which is mainly for a constant supply of power, and also allows for a little bit of rotational advantage when we go into bidirectional flow, like in a tidal environment. ORPC is also working to develop smart microgrid solutions with our deployments to help ease in communities into what renewables can be, and also provide that microgrid solution to allow for other renewables to integrate into grids more easily. Our pipeline currently exists of 4 main devices. Today I'm going to talk about the RivGen, which there is highlighted in green. We're actively developing a product called the modular RivGen, which is based on the same technology as the RivGen. It's more designed to go into tail races of canals or smaller rivers that have local infrastructure. This is supposed to be something that's, you know, easy to install, easy to retrieve, goes well in hand with local devices. Our RivGen is what we've developed for our remote community solution. It's made to be installed with excavators and fishing boats and things like that. It's a robust platform, and this is what we consider our commercial device at this point in time. We're also actively developing our TideGen. We're looking at some deployments for this in the coming years, particularly in Cook Inlet and in the Maine area. And then lastly, our Optimor device is what we consider our megawatt scale device, and that is under development still, and hope to have more information about that soon. Primarily being developed overseas right now. A little bit about our device, River Hydrokinetics. This little box right here is sort of what we call our commercialization package, if you will, with 1 or 2 RivGens that connect to a smart microgrid through a battery energy storage system or other energy storage system that work in concert with existing diesel generators. The idea here is that we can provide a base load for the diesels, provide power to charge battery energy storage system, especially in the summertime when we have excess flow. And then this also allows existing diesels to run at peak efficiency, so we don't have any issues with wet stacking, and can start to combat that as well. Slide's not changing here. There we go. Our RivGen that's installed in Igiugig is currently what we call a RivGen 2.1. It's rated at 40 kilowatts at 2.25 meters per second. It's a fairly large device. It fits on 2 flatbed trucks when it comes in. So we actually haul it out there across Williamsport and into Lake Iliamna and barge it into place where it is. The first RivGen that was installed is currently out of the water for a teardown contract. So we have another RivGen that's in its place right now. After our teardown and rebuild project, we'll have 2 RivGens back in the water in Igiugig. We're looking forward to that as a deployment later this summer. Just some quick highlights. The first one was in the water for 21 months. Went through 2 frazzle ice events. Pretty interesting seeing rocks the size of golf balls or softballs, I should say, being picked up and hurled into the turbine, and it being able to survive and still produce power on a regular basis for the village. And we also worked hand in hand. You saw previously Andy Seitz there on that mid-break presentation. He worked with us as well as some fish monitoring exercises. And there'll be more on that a little bit tomorrow, I believe, when Iggy Village President Alexander Salmon presents about some of the environmental impacts of this device. So why hydrokinetics? One of the big things that is advantageous is there's this base load power. From the previous presentations, a lot of you may have seen that there's predictable curves, predictable amounts of power that are generated year round. So, with this modeling efforts, you can actually go and look into, if you're in a tile environment, a tide book, you can look out into the future and see what your power production will be in that area. In a riverine environment, you can look at previous year's histories and kind of have a predicted model of what will come out of the river. And then our device is a little bit different than the ones that were mentioned with Ben's presentation and Eloise's presentation. Ours is underwater, so it's completely submerged. It is on top of the water for the initial deployment aspect, but once it's done, it's completely underwater. This is to mainly help with some of the issues when it comes to winter operations, where we can avoid some of the ice buildup. We do have frazzle ice events, which is a different animal in and of itself, but so far has been a non-issue at this point in time. And then the other advantageous thing is it's non-operating, silent operating. You don't hear the device when it's underwater. It's very appealing to have in a neighborhood. And the biggest takeaway from this slide, I know there's a lot of words here, but over the 20-year lifespan of a RivGen, we expect to see a 98% reduction in emissions from a village that has one installed. So this is taken into account, through winter operations, summer operations, our maintenance cycle as well. And so what we're driving for really helps drive that green solution for the transition from diesel into renewables. And partnering this with other renewables, especially with the smart microgrid, is a really advantageous solution for the future of Alaska. And that's what we're hoping to roll out here with our commercial product, which is the RivGen. So briefly on Iggy Iggy right now has diesel flown in to the village. There's a few other places in Alaska that have that as well. The plane actually can't take off unless it's able to offload its fuel. So that makes for a unfortunate situation where they have to be able to be low enough on fuel to take the entire load from the plane. The high cost is a really important bullet, 5 to 10 times the price of an average American or Canadian citizen. The diesels are just, and Eloise pointing this out on her slides as well, they're just a very high cost burden to operate these machines. So where is our site? So those familiar with Alaska, this is Lake Iliamna here on the left, and our device is at the headwaters of the Kvichak River. More specifically, you can see the village of Iggy here on the right, the airstrip there, and then our device is a little bit further downstream, fairly close to the mouth of the river. And we're behind that little island, which makes for a nice confluence of currents. Our device is assembled on site. So it comes over in pieces on barges. You can see the barge there at the bottom, and assembled right on the beach. And then from there, we push it into the water with some cranes, haul it out across the lake, do some quick tests, and then down the river to its final location. We also have a come ashore location, which is a small 10-foot connex, and that runs directly into their grid with some transformers in the area. There was a question about this earlier, working with the local populace, and this is something we definitely strive for with ORPC. We're not experts at driving boats, we're not expert welders, but the people that live in the villages of Alaska are. And there's a lot of local knowledge base that's been, in and around oil field work and local maintenance work that has been really, really key to success for projects out there. And that's the way we believe that it needs to go in the future too. These projects need to be owned and operated by the folks locally, because this is ultimately going to be theirs. We're not going to be pushing this down people's throats, so to speak. That's been a really great partnership that we've had with IGIAC, and it's been a really big key to our success. And then just to really quick, here's some photos of kind of how the installation goes. So we have our turbines that are lifted into place. You can see the deployment here with the two excavators pushing the device into the water. We're trying to use these local resources as much as we can. We have some road maintenance equipment lifting our connex into place. In the bottom right and in the middle, there's a fishing boat that's been repurposed as a barge, that's been repurposed for pushing the riv gen. So, a lot of areas that are on rivers have these type of vehicles available and this type of equipment available. And it's makes for a successful project, especially when you're going for a commercial application. And that's the end of my presentation. And there's my email. Happy to take any questions at the end or speak about anything else that WRPC is up to here in Alaska. So thank you.
Thank you, Merrick. That was very interesting. I actually manage the construction of the bulk fuel tank farm in IGIAC, so I feel like I have a vested interest there.
Absolutely.
So our next presenter is Trey Taylor. Trey is the founder and chief commercial officer of Verdant Power. He also was a speaker at that 2007 Ketchikan Tidal Energy conference that Curtis mentioned earlier, and I helped to organize that. So it's nice to have Trey back involved in Alaska, and we appreciate his willingness to contribute here. He has over 35 years of experience in marketing, including public and government relations and business development with multinational companies and major US industries. Prior to co-founding Verdant Power, he served as founder and principal of a marketing, management, and communications consultancy, creating the Interactive Marketing Institute and New Media Society of Washington, DC. Welcome, Trey.
Thank you. Let me get my presentation up. All right, can that be seen? So thanks for that introduction. In addition, I've spent a number of years on the advisory committee to the National Hydropower Association, chaired the R&D committee at NHA, and was the director of marketing communications for the Edison Electric Institute, which is the trade association of investor-owned electric utilities. So all that sort of give me a background to go into this new industry, marine renewable energy, marine hydrokinetic energy, ocean energy. It's all the same thing. It's really harvesting the kinetic energy from water currents. So let me get into my presentation up here. And so I'm going to take a different approach in having everybody, and especially young engineers or designers, understand the process to get technology correct. And it takes a long time, and it has to be patient. And there's a reason that so many technologies were hyped early on are no longer around, is because they tried to find shortcuts to the marketplace, and that just does not work. So let me explain Verdant Power's philosophy. And it's always been focused on creating something that's very rugged and simple. And we've taken a systems approach for our systems. And ever since 2002, in designing the systems, we've been working closely with NYSERDA, New York State Energy Research and Development Authority, and the Department of Energy, including all of its DOE, all of its labs. And so by taking this a systems approach, that's what we term to be our long-term competitive advantage. In other words, our whole performance is really based on a simple design, not complex systems. And that is the reason for the failures of so many other tidal turbine ocean energy systems. Everything has been focusing on, ever since the day we started, it's been focusing on minimizing CapEx and OpEx. And that's run throughout the theory, the model testing, all the patents, the full-scale prototypes. And we've been moving along now through several generations of technologies. We're now on our 5th generation, soon on what we call generation 6 or Gen 6. What we have is a commercial standard system that's tailored to sites. And our first big commercial sites will be starting in 2024, which I'll share with you. But where we started, where it all began was with the Wright project. And so let me back up a step here and share more about the generations. So, so here's a quick, I want you to keep these pictures in mind when I talk about generation 1, generation 2, 3, and 4. You can see the evolution of our technology that goes all the way back to the early 1980s. And I'm going to flip slides now. So keep these visions in mind while I flip slides to say this is how long it takes to get a technology right for the marketplace. And I'll explain what you're seeing here with this slide. So what we've adhered to is something called a technology readiness level, or TRL. And these green, so the green generation 3 and 4, I'll talk about here. And so let me explain. So generation 1 began in 1981, where the basic principles of the technology were observed and reported, and the technology concept was formulated at New York University and then verified at the US Navy's David Taylor Model Basin in Maryland. Generation 2 is where we started moving toward TRL 3 and 4 around 1985. And that's when New York University had an analytical and experimental critical functions were worked out, and the characteristic proof of concept was tested in Pakistan, of all places, with the support of the United Nations. Then DOE came out in 1995 saying, of all the technologies that are out there, this one showed the most promise for commercialization. So with my background from Edison Electric Institute and the National Hydropower Association, I grabbed it to start a company, and that was in 2000. And so in 2002, generation 3, we grabbed that report, Burton Power was formed, and then we moved forward to demonstrate a key subsystem in a relevant environment, providing validation of rotor and full scale in a water test. That's what took us to the right project site. So generation 4, from 2003 to 2009, we began working on technology readiness level 6. This means having a working prototype or full system performance, first grid connected array of tidal. This in fact was the first grid connected tidal array of turbines in the world. That was in January of 2007, operating under a new FERC ruling, which was part of a streamlining of the commercial licensing process, which Virgin Power had a hand in doing. So generation 5 then is where we are now. We started moving to TRL 7 and 8 on our way to TRL 9, which is heading to a commercial standard system by focusing on cost-efficient installation and O&M, technology performance, longevity and reliability, and environmental compatibility. So that kind of gives you an idea of the technology. So now let me focus on the contribution that all of our projects have made. And the first project, the one we're known for, is what we've been doing in the East River of New York City. So what you're looking at here in this picture is the East Channel of the East River in Manhattan. And that in the foreground, immediate foreground, that's Roosevelt Island. And if you look just down the road a little bit, you can see the United Nations building. So that's where we've been doing this. The East River is actually a tidal channel connecting Long Island Sound with the Atlantic Ocean. To know more about this project, I encourage you to go to Virgin Power's website, and there you'll see an NREL YouTube video of what we've accomplished here, and I'm about to share with you now. So what we've been doing is advancing since 2002 on the right project site. This is where we've been working with support from our business partners, which are the Department of Energy and NYSERDA, on developing a proof of concept. In 2007, that's when we had the first grid-connected array of tidal power turbines in the world, and we call that our working prototype. In order to get that operating, it required approval of 14 resource and environmental agencies requiring 23 permits. And we expect the same thing to be going on in Alaska. So we're ready to help you achieve that based on all the studies that we did. Our FERC license, which was issued to us in 2012, is literally 4 telephone books thick. And on volume 2 is every possible study you can imagine to be done, from sight, birds, fish passing, sound, all of that we have studied on the impacts of our systems on the environment. So there's something else. Here's a point I want to make, and this is a good place to pause to mention this. For infrastructure technology, it takes anywhere from 10 to 12 years to go from a working, now keep this in mind, a working prototype to commercialization. And so many technologies have failed to do that. They tried to jump the steps to get there, and that's why they did not work. They were neither reliable nor on a path to being affordable. In 2019, we completed the design of our system, which here you're seeing is actually a 1/2 scale Generation 5 system on a tri-frame mount. To explain that, in October, so how that worked is in October 2020, we installed 3 of those Gen 5 turbines, 1/2 size, on a single tri-frame at the Wright project. On this side, in this picture, you're looking at Queens side of New York City. We connected the power to Con Ed's distribution grid and averaged over 1.1 megawatt hours per day. We generated over 312 megawatt hours in 9 months of continuous operation, which is a US Marine Energy record for continuous operation of and delivering that much power. The demo project, which is a 5-meter diameter rotor, had a nameplate of 35 kW, but it exceeded expectations by 45%, receiving from Con Ed a power rating of more than 50 kW per turbine. In fact, Con Ed re-rated our turbines at 70 kW per turbine. Most importantly, the turbines performed at a better than 99% availability. This high reliability is critical to cost competitive green energy. What we have here is what we've done is we have a commercial standard system that's now tailored for ocean currents, tidal currents, and river currents. And that's what we refer to as a standard system. It has few moving parts, a fixed pitched constant speed rotor, a passive yaw system. It's readily scaled to a variety of water conditions and currents, like I mentioned, oceans, tides, rivers, even large canals. The Bong Canal in Pakistan is actually deeper and faster than sections of the St. Lawrence River. This system is designed for a 20 to 25 year life with 5-year service intervals, using no divers, no extreme heavy lift vessels. Its overall water to wire efficiency, including all losses, reached over 50%. With a focus on reliability and affordability, a tri-frame mount is designed to install 3 turbines simultaneously, which helps lower the CapEx and OpEx. And by that we mean when we use the larger systems, each turbine can be popped off and serviced on shore, sort of like changing light bulbs in a candelabra. So there'll be we're trying to minimize on-water work. And so everything is done on shore, swapping these in and out at the time. One of the things too, let's see, make sure I got this correct. On this slide 8, this is really important. Something else that we've been able to achieve is we had our system commissioned, and that was the final commercial step in getting through 7 and 8 and all the way to 9, is having a commercial step is operating over a range of conditions to advance through those TRL steps, whereas the actual system has been completed and qualified through test and demonstration. By focusing on maximizing the system power performance, increasing availability and reliability, and in reducing project cost, which includes installation of in-water instrumentation to measure a water velocity, accepting testing of the SCADA system, which is the supervisory control and data acquisition, and undergoing a power performance assessment by the European Marine Energy Center. So that's what's gone on. That's what we did at Wright. EMEC, European Marine Energy Center, EMEC, is the first marine energy test laboratory to have designed or have been designated with Renewable Energy Testing Laboratory, an RETL status, by the International Electrotechnical Commission, or the IEC. Verdon's tidal power turbines are the first in the world to be assessed by EMC as an RETL, and has received international recognition from the Renewable Energy Test Report, verifying compliance with formulated international standards. No other companies achieved that in the marine energy. Verdon Power has. This will serve to underscore buyer, financial, and insurance confidence in Verdon Power's systems. So what we have is the world's first third-party measured to IE standards. Where Verdon Power is now, we're underway with a new financial raise for the company, where we'll be scaling from that 1/2 scale 5-meter rotor to 12 and 18-meter size rotors, which we call the 18-meter class system. This will be our Gen 6 turbine. We're advancing to full commercialization. We're hiring staff, and we'll be establishing international supply chains. That will take us to, I mentioned the Wright project being one. We have 4 other projects now shaping up 2 of them in the UK and Wales, and 2 in the United States, 1 being Alaska. So I'm sort of working up toward Alaska here, how we get there. On all of these sites, what's really required is doing what we call a resource assessment and feasibility analysis, or RAFA, out of which then comes a business plan for execution. And that's how you, so the earlier panel was talking about how do you track money. It's really putting together the financial models for each project and the LCOE for not only the technology, but for the project itself. And that's how you begin to put together a business plan for developing a project. So let me talk about these 4 projects and how we get there. So let me first begin with a project we're going to be doing in Wales at a place called Ramsey Sound. And we're taking our 5-meter diameter rotor that ran successfully in New York. We're refurbishing it and we're shipping it over to a company in Wales. They'll be installing it on an they already have the consents, the mounting system's already there. So we're putting that 5-meter diameter rotor on that system near Pembrokeshire in Wales. It will operate and deliver power there for several months, installed on a ready-made mount. So we don't have to worry about installations because all the consents are in place for that. And it'll be followed by a test and demonstration of our generation 6, which will be a 12-meter diameter rotor rated at 330 kW per turbine. So we'll be going from 1/2 scale demo project, the Gen 5, to full-scale commercial project with the 12-meter diameter rotors rated at 333 nameplates. And so 3 on a single tri-frame, that'll be a 1 megawatt system. So that's how we're approaching the UK. It is 3 larger turbines on a tri-frame, 1 megawatt system. So, and then near Ramsey Sound is this place called St. David's Head, which you've already done a preliminary analysis that could support 10 megawatts. In other words, 10 1 megawatt tri-frames. The annual energy production of that project would be 20 gigawatt hours per year. Our second project, so then what we learned there by scaling up at St. David's Head and Ramsey, we're moving toward Holyhead in Wales. This is in the Irish Sea. And we've been working with Marine Energy Wales and Mentor Mon, the management company of the Morlice project, since 2016. And the Morlice demonstration zone, MDZ, in West Anglesey at Holyhead is in the Irish Sea. The MDC, or Morlice, has a potential of at least 240 megawatts. Verdon Power is one of 8 berth holders at Morlice and will develop a 30 megawatt project for starters. During this next period, various aspects of the project will be undertaken by Mentor Mon, including grid interconnection and a 2-year zone consenting process, while the company will be conducting a RAFA on our particular berth that leads to 30 megawatts, or the subzone, allowing us to assess the feasibility of a 30 megawatt commercial project. Verdon also will be bidding on something called a contracts for difference during this 4th round, or it's called AR4. And this is like a feed-in tariff. And the company will also be seeking support for this early stage effort, as well as for front-end engineering design, or FEED, as you know it, that would support the development of plans leading to a potential project investment decision by early 2023. Now, then at that point, we'll be installing 2 1 megawatt tri-frame systems of 6 turbines for system operations by 2025. This will be a final commercialization step demonstrating the system's simplicity, robustness, and scalability, making it suitable for varied tidal projects and as arrays. With commercialization, the company plans to install the balance of 1 megawatt tri-frames for a total of 30 megawatts by 2026, with an annual energy production of 60 gigawatt hours per year, and expand our supply chain to include the UK. And the UK's tidal potential is 11 gigawatts that's been identified with preliminary assessments to date. Now, the reason we're heading to the UK is because there is such things as feed-in tariffs and subsidization and revenue support. So while our technology costs are high, we'll be going to the UK to drive our technology costs down, and then we're pivoting. And by pivoting, that means we're heading right back to the United States. And one of the first projects in our crosshairs, if you will, is in Long Island Sound. And this is, and so the company will be conducting a RAFA in Long Island Sound, which we'll call the Long Island Tidal Energy Project, the LIGHT project. The LIGHT project has a potential of at least 500 megawatts. We think even more. And at 500 megawatts, the annual energy production of our systems has been verified by EMEC in Europe, will be 1 terawatt hour of electricity per year. taking a phased approach as being done in Wales, with 2 megawatts being installed in early 2025, then to be followed as much as an additional 23 megawatts by the end of 2025. By the end of 2030, we expect to deploy the turbines for a total of at least 250 megawatts, which will have an AEP of 500 gigawatts per year. This will be the first utility scale deployment in the US with lower tech costs affecting 3 states. That would, in fact, 4. So it'd be New Jersey, New York, Connecticut, and Rhode Island for 2 purposes: for clean energy generation and for clean hydrogen production. Since passage of the Infrastructure and Jobs Act, New York State is moving to establish a clean hydrogen hub at the direction of New York State Energy Research and Development Authority, the Empire State Development, which is the economic arm of New York, and New York Power Authority. So that, with all of that, we are now ready to really bring something we think to Alaska. And so I'm serving the best for last, which is Turnagain Arm Tidal Energy Corp project at Cook Inlet. Now, what I love about this photo, I don't know if you can see it sharply enough, but if you look really closely at this tidal bore at Turnagain Arm, you see that dot in the middle of that wave? That's a surfer. And I think that is just so cool about the kind of tidal power you have at Turnagain Arm. According to DOE, Cook Inlet has a tidal power potential of 18 gigawatts. The Turnagain Arm Tidal Energy Corp project might have as much potential as 1 gigawatt. That's to be determined, because you have to get in there to do a proper RAFA of the water potential. But like other projects, it will begin with a phased approach at point possession. Verdant Power has formed a JV with Tidal Energy Corp, which has offices in Anchorage, to conduct a RAFA study. And as with the company's successful Wright project in New York City, TEC and Verdant will be taking an inclusive, transparent, and adaptive management approach for this RAFA. And we would like to get that underway as soon as 2022, once we have funding identified to pay for that RAFA. So we're looking for that funding to get going. And this will be for an initial 10 megawatt project, which will produce 20 gigawatt hours per year. It would be followed then by a front-end engineering design and grid consent for 2 to 5 megawatts to be installed by 2026 at the latest. And then the remaining 5 to 8 megawatts will be installed in 2027-28 with funding and success of that first phase project. But here begs the question, how much more could we do by 2030, given how much power there is to tackle? The tidal power potential of Cook Inlet would not only make a significant contribution to the renewable portfolio standard for the rail belt of 30% by renewables by 2030, and even higher as you start going out, that the 5 utilities are going to be required to buy as renewables, but it also could power electrolyzers producing clean hydrogen for rural communities, military bases, and even export. Alaska's tidal power potential, as you probably know, is 50 gigawatts. So keep those numbers in mind, 50 gigawatts. Because also consider this, for every gigawatt that's produced, it creates potentially 1,000 full-time jobs, offsets 6.7 million tons of coal per year, and eliminates 1 million tons of CO2 per terawatt hour per year. The UK has a potential of 11 gigawatts, which has really excited the world, but Alaska has 50 gigawatts. What a resource to tap, and what a potential Alaska tidal power can make to the world. So that's what I wanted to share with all of you, and we're excited about getting our technologies underway in Alaska. Thank you.
Thank you very much, Trey. That is really exciting. I would mention that the average load on the rail belt grid is about 550 megawatts with peaks of 850. So we might even be able to use some of that power for heating purposes, or as you said, hydrogen production. So our next presenter is Oliver Ragg. He is the commercial director at Orbital Marine Power. With 15 years of experience in clean energy and science, he has facilitated the raise of over 180 million pounds of funding to back the development of innovative technology to enable the energy transition. As a leader in the ocean energy industry, he holds board positions on both the UK Marine Energy Council and European trade body Ocean Energy Europe. Welcome, Oliver.
Hi, thanks so much, David, and thanks so much everyone for inviting me along today. To give you a bit of an update from what we've been up to at Orbital Marine Power. So at Orbital, we're developing this floating tidal turbine solution. So a bit of a different vision for what tidal energy looks like to what maybe some people may have seen, and it's a bit of a I suppose iconic bit of engineering we think of the 21st century of what we're looking at here. Just in terms of just to throw this up there so people can understand kind of how the technology works and what it looks like. It's this main hull structure in the middle, and then we've got these retractable legs on either side where the turbines sit on each end of the legs. And the focus on this is very much on reduced levelized cost of energy. And that's really what the company's been working at. As Trey said, the past 20 years or so that Burden have been at it, I can definitely purport that that's the amount of time it takes to develop some of this stuff. Orbital's been at this for over 15 years. I think the first grid connected machine that the company had was actually whilst I was working at the European Marine Energy Centre, and that was of a 250 kilowatt floating platform. So the first floating grid connected platform and for tidal energy installed anywhere in the world. But in terms of a briefer kind of history and initial look forward for where we're at with the company and what we've been up to, so kind of going from left to right across the screen here, we can see that in 2018 we finished the test program of the SR2000. So that machine was a 2 megawatt prototype. As I said, that followed in the wake of a previous 250 kilowatt machine that had then been from previous deployments as well. Over the course of a 12-month period, this machine produced over 3.2 gigawatt hours to the UK grid. So this was really, I suppose, a full-scale demonstrator, as we termed it, kind of at commercial scale. It really hit and broke down quite a number of barriers in terms of the amount of power produced from a single machine. At points, it was actually reaching 25% of Orkney's electricity demand, which is a group of islands of about 20,000 inhabitants off the north of Scotland. So that machine itself received 2 awards, the Institution of Engineering and Technology. And off the back of that, we were able to raise additional grant funding and support for our next iteration of the technology. So there was, I suppose, what we call some steps between the SR2000 on the left-hand side and the O2 in the middle, which we would call, I suppose, that's our commercial machine. There's some fundamental innovations that were brought into play with that machine. Probably the most critical of which is the leg retraction system. So that bit that I showed in the previous slide, where you can see how the legs kind of get lifted up either side of the turbine. So in a gull wing style, I kind of liken that, it's either like a DeLorean from Back to the Future or like a Tesla Model X, depending on your cultural reference point. But I think they're both kind of, you get a picture from that. Okay, so that's the fundamental innovation that we've proven out with the O2, which is in the middle, and that's got a pitching hubs so that we pitch the blades for maximum energy extraction. Also, what I suppose the machine in the middle is what we are terming a commercial demonstrator. Okay, so a critical step change that we've happened with that technology is that's been funded with construction debt finance. So that's had £7 million of construction debt finance, albeit from a fairly non-standard format. It's come from a crowdsourced platform called Abundance, which is a crowdfunding platform in the UK. So that's at a £7 million construction bond, which is soon to be refinanced into an operational bond. The project does benefit from 5 ROCs, which is the Renewable Obligation Certificate. It's a legacy renewable support mechanism in the UK, which means we're securing approximately about £250 per megawatt hour for that project. But that turbine will stay in the water until 2037. And so, in 2020, we completed the construction of the machine. Even in the height of the pandemic, we still managed to get the machine in kind of on time and to budget. And it was launched in 2021 from the Port of Dundee. And one of the things that we find really interesting from I suppose, looking at the development of tidal energy is a lot of this is in kind of peripheral coastal communities. And there's a huge opportunity for kind of economic regeneration. And so this was the first vessel to be launched out of the Port of Dundee in 40 years. So huge kind of coup and benefit for the region. Also in 2021, we're busy raising additional finance. So we raised £2.4 million of new equity from Crowdcube, again a crowdfunding platform, but this time it was equity direct into the company rather than a construction bond. We also secured investment from Technip FMC. So for those of you who know, Technip FMC is, I suppose, what you'd call a tier 1 oil and gas contractor. So they're building the oil and gas platforms for Total, BP, Shell, Chevron, etc. And basically Technip had taken a view across the sector and reviewed opportunities for offshore renewables. This is part of the energy transition in action that we hear about, and they selected our technology platform as basically, as far as they were concerned, this was the way that you made tidal energy commercially viable. We also secured in 2021 additional backing from the European Commission with approximately an £18 million grant to develop the O2X, as we're dubbing it at the moment. And so that's the next iteration of this machine. I'll come on to that a bit later. And it talks a bit about how we see the energy system of the future. There's been talk about kind of green hydrogen and so on and so forth, and we'll talk about that. So moving into this year, what are we focused on now? We're growing our global pipeline of commercial project opportunities, which clearly does involve a focus on Alaska and a keen interest that we have in the area. We're soon to be kicking off some feasibility work, looking at different locations and how we would go about developing the consenting strategy for such a project. We'll be looking to secure contracts for some of our first commercial arrays, mostly in the UK, and again very aligned as Trey has his finger on the pulse in the UK. We're looking at some of the projects in the UK as well. And then I suppose kind of beyond 2022, we're looking at that wider kind of expansion and securing additional projects and locations. But a bit about the technology and why it kind of looks so radically different. So the first bit is pretty much looking at the construction and repair, and it's that focused on levelized cost of energy. So it's the cost to repair. Basically we can just get the guys out on a boat, they can jump onto the turbines, fix them pretty quickly, if not quicker than you can on a wind turbine, because a lot of tidal resources are closer to shore than offshore wind. So the cost and time to repair is a lot cheaper, and also the cost to construct is a lot cheaper. Bearing in mind, obviously, as Trace mentioned, with some of the turbines that they're looking at, they've got the ability to use smaller vessels. As you scale up larger turbines, you get heavier, you need bigger cranes. But by having a floating system, we're able to scale up to have larger turbines, but we avoid these large vessels. Now, the other point that's incredibly important about this is the operational benefits that we have. And I was really pleased actually to see some of the slides that Levi put up earlier. We've highlighted specifically the issue with the turbulence. So that 10% turbulence, you can keep within that with maybe about 30-40 meters of water depth here. And this is a fundamental principle that we play to our advantage, because the water column at the bottom, the water moving at the bottom of the water column, there's higher turbulence there, but also it moves slower. So it's a bit like in wind energy, you need to get turbines high enough so they kind of punch through the wind envelope, as they say. And we're placing our turbines in the optimum resource possible. So it's a fasting flowing resource, and it's the most kind of laminar. We're avoiding all of that turbulence. And so kind of at that scale, we're increasing the yield and we're getting maximum swept area. So they're the kind of the fundamentals that have driven a lot of this concept for this kind of the piece of engineering that you can see at the moment. And just quickly, in terms of the SR2000 and what we achieved with that, as I said, kind of over the course of the year, it was 3.25 gigawatt hours. And it produced a really kind of good constant supply of electricity at just under 25% operational capacity factor for the machine over the course of the entire year. And that's taking into account all of the downtime that we had. Now, one of the things that we look at is we accept that to increase our performance and our yield, we're going to have to access the machines for maintenance. Much like, there's no wind turbines at the moment that you can install and leave to run for 5 years. You have to have annual maintenance. We believe that putting that maintenance strategy in place is the right approach for tidal energy. Now, the graph that I've put up here shows you the cumulative energy production from the SR2000. And you will notice, and maybe apologies to anyone who's seen this slide before, but you will notice, these kind of leveling off points, where the line's going flat for a while, we're flatlining. Obviously, we're not producing electricity at those points, but it just goes to show, if we've had faults, we've been able to get out, we've fixed them. We fixed them, within short periods of time. The quickest fault that we had, I think, was about 45 minutes from identifying the problem, getting onto the turbine, and then fixing it. Again, the point is, if you had a large 2 megawatt system on the bottom of the seabed, you've got to wait for a longer weather window. You've probably got to wait for neap tides, so you've got bigger slack tides, so you can access the machine. You've got to account for any exposed sites. You've got to account for the wave regime and so on and so forth. So we're able to address some of those, and we've got some really positive power production figures off of the SR2000. But as I said, we've moved on from that now, and we're on to the O2. And this machine produced first power to the UK grid in July 2021. We've been working through some of those big steps between the SR2000 and the O2, and specifically looking at control systems and pitching blades and tracking the power production from the machine across what we predicted it with, those predicted power curves, looking at all of those sorts of things. So basically running it through a commissioning process at the moment, which I'm very happy to report is going incredibly well. For the system, we've hit peak power output at 2.2 megawatts. The MES power we've had from a single flood or ebb tide has been 7 megawatt hours, and the most power we've produced in a day has been 26 megawatt hours. So we're hitting over 50% capacity factors at spring tides here. We're collating all of this data at the moment, and we're looking forward to reporting soon on kind of that wider piece, looking at the production of the machine over monthly cycles, so that we can inform people about that and look at not just weekly capacity factors, but to bring that out and provide more information to people on that. And as a whole, I think it's really important as the tidal energy sector, as Levi I think was saying earlier, in terms of our stages of development, kind of seeing is believing, and numbers speak. And I think it's more important that people keep on publishing this kind of data, so that companies can understand just actually there are some technologies out there that are progressing very well. And another thing, in terms of kind of seeing and believing, this is the guys out on the turbines. What we're doing at the moment here is practicing replacement of a brake on the pitching systems. That's about 100 kilos payload. That we're basically practicing a maintenance interval at the moment. So through some of the grant funded projects that we have at the moment, again, previous projects, we're running through a maintenance program, which enables us to de-risk a lot of our maintenance activity for when we move into commercial projects, and we can prove to people how that works. Now, one of the other things that I just wanted to talk about, again, kind of a bit of the elephant in the room, I think, with tidal energy is cost. Where are we at cost? How much does it cost at the moment? Where are you going to get your cost reductions from, and how are you going to get there? So again, kind of much better to be upfront and to look at these things. And so as I said, we've addressed a lot of the fundamental innovation with the O2, and what we're moving now on with the O2 system in the water at the moment, what we're moving on to now is a process really of incremental innovation. And this is a critical part, because this is where you get to really drive down those costs of energy, where you've gone, okay, we've got a system, we know that it works here, we know that the fundamental hydrodynamics work, we know that the power is being produced from it. Okay, right, let's work on optimizing this. But we've got a product now that is commercially viable, but we can make it better. Like we've seen in offshore wind, you know, the guys in offshore wind have, you know, basically what you're seeing, you know, to the untrained eye, you know, from a distance, or or put it in perspective, you know, a 1 megawatt wind turbine or a 10 megawatt wind turbine, it's a stick with 3 blades on the end of it. You know, but there's been a lot of innovation to get to that point and changing cost reduction. What we're going to see here is basically a similar sort of system for the orbital technology, where we'll be looking at things like rock bolting anchors, optimized O&M systems, increasing rotor diameters, advancing our pitch control system, blade design, powertrain optimization, you know, so on and so forth. So you can see on this slide, there's these number of innovation steps that we'll be taking to drive the cost down. But the other thing, and as a lot of people will know, is you've got to work with economies of scale to drive this sort of stuff down. So broadly, you know, our costs in line with what we've seen produced by a lot of reports in the UK, in and around maybe that kind of £250 per megawatt hour, where we were with the O2. We're hoping to drive those costs down further. Interestingly, the blue that you can see on here at the moment is actually the forward-looking contract price range for electricity in the UK over the next 2.5 years. So if we could go out and get PPAs for that time. Now, obviously, that's not what it's going to look like over a 15-year period, and we know that offshore wind, for example, has been contracted at a much cheaper price, and we know that obviously the cost of energy in terms of, you know, wholesale electricity supply in Alaska is a lot below that. So what we're doing is we're working to drive that down at the moment. A lot of this work, or all this work actually on cost reductions, being completed by engineering consultancy Black & Veatch. And so we estimate that within the region of under 500 megawatts of deployment, we're getting projects in the water at under £100 a megawatt hour. Now, apologies to my side, I've not converted that into US dollars, but I'm sure it's not too complicated a calculation. You know, at fast speed sites, and when I say fast speed sites, to be clear, again, looking at the data that Levi's presented in Alaska, you know, we're talking fast speed sites in the Cook Inlet, and so we're looking at price point in and around kind of £60 a megawatt hour is where we'd be hoping to get to at some of those locations, you know, with that scaled up optimized turbine. And then the question kind of becomes like, okay, so at what point do you want to kind of jump on that price curve? We've been working very hard in the UK, and, you know, as Trey said, we've got a pipeline, a growing pipeline of close to 100 megawatts of projects in the UK that we're working to, and so, you know, we're very keen to look at what happens in Alaska and at what point the entry point is there. Is it, you know, go and deploy 500 megawatts somewhere else and come back to us in 15 years, 20 years time, or is it, okay, well, actually, let's accept that maybe there's some more learning to be doing, you know, looking at the Cook Inlet resource, and maybe it's a smaller project at a slightly higher price that gets subsidized in some way or something like that. You know, there's options to look at this. In terms of our technology development, in terms of what it looks like in the energy system of the future, and I said I'd talk about this a bit earlier. So the EU grant funded project that we have, Forward 2030, is developing the O2X turbine. That should go in the water in 2024. So we'll be awarding contracts for that middle of this year. You know, there'll be more pictures of us cutting steel and so forth and all that good stuff that we should be doing as turbine developers, hopefully by the end of this year, which we think is kind of great momentum, having had the O2 just deployed last year, you know, and then within a year's time, we've already contracted the next machine to move forward. That's going to be installed up at the European Marine Energy Centre alongside the O2. That will create a 4 megawatt plus array that we'll be seeing in there. That will be producing in excess of 10 gigawatt hours of electricity a year. Now, the really interesting bit comes with that. Obviously, for us as tidal turbine developers, this bit in the water is very interesting. But for a lot of other people looking at the energy transition as a whole, what's happening onshore is equally as interesting, because at the substation that EMEC use, there's also a constrained community wind turbine, and the grid on Orkney as a whole is constrained. There's too much wind energy being produced there. So what EMEC also have is a vanadium flow cell battery, which is being installed this year, and an electrolyzer, which is installed on the site. And so what this enables us to look at is, okay, well, what's the optimum solution for tidal energy. You know, at what point do we produce to the grid? At what point do we store the electricity? At what point do we produce hydrogen? And we're working with one of the largest European utilities, ENGIE, to look at this, and they're going to be modeling this out. You know, whilst we'll have this system running kind of at a demonstration scale, you know, with a 4 megawatt plus array installed, ENGIE are going to be modeling that up, looking at what happens when you have multi-100 megawatt tidal energy projects combined with wind energy projects in large parts of Europe. And again, something that's potentially transferable across to the European grid. I've just thrown water all over my laptop, by the way, so I'll just be, you know, full disclosure there in case my laptop does blow up on me here, which hopefully it won't do. But anyway, that enables us to decarbonize both the you know, domestic heating systems, but also some of the harder to decarbonize systems, such as, you know, heavy industry and also marine transportation. Last but not least, the final piece for me to just kind of throw up is it's all well and good us doing all of this, but we still have to have an eye on actually what our carbon footprint is for these machines. You know, we've seen, and sometimes I kind of wonder about this. You think, well, you're producing renewable energy, isn't that enough? And it's not. You know, in Europe we have huge problems now actually with the amount of wind turbine blades that aren't being recycled. So we've got a keen eye on what our carbon emissions equivalent per kilowatt hour are, and we'll be working to try and drive that down over time as well. So that's a roundup for me, an overview of what we've been up to at Orbital Marine Power. Happy to answer any questions during the Q&A that we've got now, pending that my laptop doesn't blow up on me.
Thank you very much, Oliver. And I think maybe knocking over your water bottle was just demonstrating a new kind of hydrokinetic technology, or maybe making sure everybody was paying attention. But
I think one of the two.
Yeah, thank you very much. That was a very interesting presentation. Before we get into some of the questions in the chat, I want to make sure we address Bill Lady's question that came in under Q&A. Regarding the Indian Islands near Glacier Bay in Southeast Alaska, because I have an answer to that. The Electric Power Research Institute actually did a very nice job of characterizing that resource in about 10 or 13 years ago. I have that report and I'd be happy to share that with you, Mr. Lady. And I would mention that Southeast Alaska gets about 95% of its electricity from hydropower. So there's a bit of a challenge there. In any case, I want to go back to some of the questions in the chat. And let's see. So there were a couple early on for Merrick. This one's from Jeremy. Can you provide a timeline for the IBC project? How long did permitting take? When did engagement with the community start?
Yeah, good question. So that project started in earnest around 2014. There's a couple iterations on designs, and initially that was operating under what we call a FERC preliminary permit. So that's a permit where there's, you know, some certain requirements as to what can go to shore and what can't go to shore, what kind of devices can be in the water. IVC, Igiaga Village Council, was awarded a preliminary permit, or sorry, a pilot permit, I should call it, in 2019. That's a 10-year permit with a capacity cap on it. So that, you know, in 2029 or so, they'll be looking at renewing that for a full commercialization permit. And then similarly in Cook Inlet, and, you know, Trey alluded to this a little bit as well with Tidal Arm, Turnigan Arm Tidal. Those permits that we're currently looking at there, those are FERC preliminary permits as well. So those are 4-year permit for the time being. And then, you know, hopefully when we get into the end of that 4-year period, we'll be looking at going into that pilot project aspect.
Thank you, Merrick. Another one for you. Did you reach out to Igiagic, or did they contact you originally? How did you navigate building this relationship?
Yeah, well, it started off with a conversation in the gymnasium there at the local school in Igiagic. And that was with my predecessor named Monty Worthington. But there was kind of a mutual understanding, I think, when that first started. So But definitely started with like a, go out to the community, do a show and tell about what the product and the technology is and how that can take off.
Yeah, and I will say that Igiugig is a very impressive small community in rural Alaska. They're very forward thinking. I worked with Alexander's father many years ago, and even back then it was an exceptional place to work. So here's a question for Trey. What are the plans for Verdant Power's technology during winter ice season in Turnagain Arm?
Well, we haven't gotten there yet. When you do a resource assessment feasibility analysis, it usually begins with gathering all the existing data, studies that have been done to find out what more needs to be studied. So all that can be going on during the winter months. And then what happens is during better times, we actually get out onto the water to do a survey of the water currents. We actually map that core current, which is about a third below the surface. And then we do sediment gathering, all kinds of studies. And that's what there's 10 tasks that we go through when we do a study. And so if it's bad weather, we just don't go out there. Just other things we could do.
Great. Here's a question for all the panelists. So maybe I'll direct it to Oliver first. Can you comment on any grid services marine energy provides compared to less expensive technologies such as solar or wind that may favor marine energy in some cases?
Yeah, very happy to answer that one, David. I'm hoping that I'm still coming through to you and that you can hear me okay.
Yes.
The one of the things that you've got as a benefit for tidal energy specifically is obviously the predictability of it. So you can look at this and you can predict out into the future where you're going to get your production and how that's going to come through. The other thing that it's got a huge benefit in, and I suppose I'm looking at it because I understand the UK energy system a bit more, and I'd have to look at how that ties in with the Alaskan energy system. But in periods of time, there's some weeks in the UK where in winter, it's very, very calm. There's not very much wind, and maybe there's a lot of cloud cover, so you're not getting hardly any electricity from wind or anything from solar. So all of a sudden the price of electricity goes exponential. So we found prices in the UK in the last 24 months that have gone in excess, at some point in excess of like £2,000 a megawatt hour. So based on that's like $2,600 a megawatt hour for some points. Now, I'm not saying that that's long periods of the day, but it means that you can access that kind of higher value energy, as it were. Because also what you get is so because the wind and the solar guys, they can't access that, because when it's windy, they're producing electricity, but effectively you get this process known as kind of price cannibalization. So they're actually cannibalizing and driving down their own costs. So there's lots of wind, they want to produce electricity, but all the other wind turbines do as well at the same time.
I could add to what Oliver was saying, if I may. Not only predictability but reliability. We are working with possibly with Con Ed about energy storage, because tidal power is so predictable and reliable. Con Ed would know exactly when to pull on energy from batteries and know when those batteries are going to be recharged, and that's another value to tidal power.
So Trey, you've just sparked another thought that I've had there that I should have mentioned, which is and it was brought up earlier. This point about green hydrogen is that if you have a tidal energy installation associated with green hydrogen production, it's actually easier for you to predict the amount of hydrogen you're going to be producing, and then the amount of storage that you're going to need. And one of the things specifically we're looking at EMEC is what happens if you put a battery between the tidal turbine and the electrolyzer, and then you can manage a more steady state of hydrogen production. And that then reduces your operating costs on the electrolyzer, because you're not kind of jumping up and down with these spikes of energy that are going into it.
Thank you, Oliver and Trey. I would mention one of our experiences integrating renewables is that cheaper, lower tech integration is often a good solution. In rural villages, we used dispatchable thermal loads to control frequency. But on the Alaska Rail Belt, we have kind of an ace in the hole, and that's something that Curtis Thayer mentioned earlier. The hydro project we own has an average output of 45 megawatts a peak, about 100 or 110. But behind the dam, there's 200 gigawatt hours of storage. And so it would actually allow the integration of significant renewables. And if the rate of change of output of the renewables is slower, as tidal is compared to solar particularly, then it has less of an impact on the O&M cost at the hydro. So I have another question for Trey. How do you plan to address sediment deposition and movement in Cook Inlet? Is there a concern of the turbines being potentially buried? But maybe your earlier answer also addresses that one.
No, it's a good question, because in Turnagain Arm, there's lots of sediment. And that's why we picked point possession, because that's where there's the least amount of sediment. And so more than likely, where there's lots of heavy sediment, we wouldn't put our turbines there because they're bottom mounted. But for orbital, it could be good places because it's all at the bottom and they're at the top. So there's ways you could do it, approach it, but we would avoid sediment is what we would do.
And I'll also add to that, there are certain places in Cook Inlet that are considered self-scouring. So, you know, the bottom may have a pretty constant profile just due to the extreme velocities that come through it, which would, you know, lend to a bottom mounted device being a beneficial installation.
I believe point possession has been mentioned as a potential spot for a second transmission line across Cook Inlet to the major loads in Anchorage and further north. So that might be another reason to look at it if there's a substation planned. But that's a long ways off. So Merrick, do you have any idea how much diesel has been offset in Igiugig by the operation of your device?
I don't off the top of my head, sorry. We're putting out constant power onto their grid. In the past 2 years of operation, we didn't have a microgrid controller, and so that's part of our installation this year. And so we self-limited what power was put onto the grid in order to not have their diesels operate in like a wet stacking mode or inefficient manner. So we were limited to about, I want to say maybe 30% of their grid load. And so in the future, when we go into that, we're going to be using that battery energy storage system along with those smart microgrid controls to be able to put full output onto their grid. And then we'll see some real savings. Predicted to see somewhere between 60 and 90% once the full system is operational throughout a full year of operation. So definitely be able to speak more to that as we progress with the project. But as of right now, I don't have that number off the top of my head.
Let me add something to what Merrick was saying. I just attended a webinar on hydrogen production. There's predictions that by 2027, fuel cells and hydrogen will be cost competitive with diesel gensets. And might that be an answer for so many villages in Alaska?
I think that's a great application, especially in Alaska, especially in the villages where maybe the rivers are completely frozen in the wintertime. You might be able to have some excess production in the summertime, assuming there's no environmental impact to their local resource in the area, and kind of get into like a cyclic loading of how power can be produced and maybe a change in the landscape, but definitely a little ways off from where we are with the current technology anyway.
Yeah, you can actually operate diesel gensets with injection of hydrogen or ammonia. It's been done successfully. In fact, we did it at our shop, and there is significant improvement in emissions as well as diesel fuel efficiency. So that's an interesting concept. I think the economics are yet to be determined. One of the things, I'm a mechanical engineer, I'll confess. So one of the things I'm most interested in is the O&M costs, and you each have different approaches to hydrokinetic, but I would like to ask each one of you, what do you expect your highest operation and maintenance cost will be, and how do you plan to address that?
Can you go first for
Please.
that?
Yeah.
I mean, I think, so we look at the wind energy industry, looking at, well, where are their costs coming from, and where do you get the big bits of downtime? There's a really good report that was produced under a European funded project called Wind, and in that project, there was, and this was a point where you had probably gigawatts of offshore wind installed and onshore wind, right? So they were looking at where all the faults came from, and the big faults that we're going to see are going to be in the drivetrain. Yep, and it's going to be generators and gearboxes. They're the big hefty stuff that even we will probably remove devices from site to change some of those sorts of things. We're trying to work on that, and the cost-effective way of doing that is taking the turbine up and then running it up a slipway. So again, we're not using any heavy cranes for the deployment or retrieval or any of that sort of stuff. Now, why gearboxes and generators are expensive in any case. They also have long lead times. So for the scale that we're at, 1 megawatt plus, you're talking 12, 14-month lead times from ordering these things to having them ready, which at this early stage of development creates an issue when you're looking at strategic spares. I mean, it's something that we're running through at the moment with the O2 up on site. We have an operations base up there, and we hold a bunch of strategic spares, but we're talking with a number of our suppliers saying, right, well, which of these bits do we actually need to buy? Do we need you to buy and hold on a shelf? Do we hold on our own shelf? But yeah, I would, and then actually a maintenance strategy for us is like, right, okay, well, what do we do? Do we actually build, full nacelles that, okay, we could maybe even in the water, because we can install and remove the blades in water. So we've done that test, as it were. The way the machine is designed is actually you could do that with the nacelle as well. But so we could have a whole nacelle that you removed one and just bolted the next one onto it, or is it bring it onshore, open the thing up and replace it all? And it's going to be like an economies of scale thing. So once we get to a project of a certain size, actually having just a spare drivetrain to one side, and then we swap things out and then we recondition another one so that we've got it ready to go. That's going to become something that's viable for us to do, and ultimately that's going to improve the uptime of the whole project in any case.
Thank you, Oliver. I notice we're just about out of time. Jeremy, do we have time for Merrick and Trey to address that question?
I think we've got a little bit more time.
Okay, Merrick?
Yeah, the one thing I would say is with ORPC, having gone through 2 summers of maintenance on our device, Nigiyagig, especially having ended our current DOE contract to bring that device back to Anchorage, there's a lot of personnel costs that goes into operating in remote villages. And I think, for us right now, that's kind of one of our larger expenses when it comes to maintaining these pieces of equipment. And so kind of changing that landscape and having the people that live there be the customer owners of the device and trained in operations is really going to be one of the bigger cost saving methods for us. And so we're actively doing that. We do have some folks that are getting trained up on operations. Last year we did it with just 2 people from ORPC out on site, which was pretty significant compared to the first year when the device was installed and there was a whole crew there. So that's going to be one of the bigger drivers for us going forward, I believe.
Great. Trey?
Yeah, so for us, as we scale up to larger sizes, 12, 18 meter diameter rotors on a tri-frame, our plans are to have a floating tri-frame. So it's floated out into position, sunk and grouted. And then each turbine is on a cable. So it pops to the surface when it needs servicing or repair. So on shore, we'll have an assembly plant where components around the world come together for final assembly, but it'll double as a service and maintenance depot. And so when a turbine, so it's like changing light bulbs in a candelabra. So when turbines need a tugboat, just pull out the new one. The old one's up to the surface on it's called stab and plug system. It's hooked up, socked back down, and then the old one, or the one that needs refurbishing or repair, goes ashore. So that's how we plan to keep O&M costs. On water work, as everybody will tell you, it's very expensive. So we're trying to minimize that.
Great.
So anyway,
Thank you.
that would be our approach to keeping O&M costs down.
Yeah. Jeremy?
Well, just wanted to thank everybody again. Thanks to Oliver, and especially for Oliver. It's a late night there, I know. and then Merrick and Trey, as well as our panelists in the earlier session. So thank you very much. And I'll just wrap up with a few concluding thoughts. I think we've seen kind of the full gamut of current energy technologies today. We also heard quite a bit about how changes in financing have progressed. That's pretty refreshing to hear, as a longtime industry watcher. I know the UK is quite a bit ahead of us in that sense, but we have some promising developments in our end too, in particular the proposed RPS standards in Alaska, and then the proposal of a green bank as well. So I'm hopeful that we'll start seeing some of these financing schemes progress from more of the grant-oriented focus where it was in earlier years to more of these mature type financing schemes, bonding, that type of issue. We also heard a lot about hydrogen. We know that's, with the infrastructure bill, there's quite a lot of emphasis on clean hydrogen. So I think that's a theme we'll be hearing throughout. And just to plug for our workshop, we have a workshop on hydrogen in about a month from now, I believe. So basically, what do you do with all that excess energy? We also heard that there is a lot of energy in Cook Inlet, so that's definitely promising, but also in our river systems as well. Another thing I would like to highlight is Trey brought up the IEC standards and certification by EMAC. Department of Energy in particular in this country has put a lot of work into developing those standards. And there's a number of folks on the line who I think have participated in that process, including myself. And so that's another indicator that the industry is definitely moving towards maturity in that area. 12 years ago, those standards weren't there, and now there's some standardization process. So it's helpful with the financing and the project development side of things for sure. Those are the main highlights that I got from today. I'm sure I'm missing a lot, but basically wanted to say thanks to everybody. Well, so we saw kind of a full range of what's happening around current energy converters in the US and Alaska, and then definitely got a short glimpse of what our colleagues are working on in Scotland. If you do have the time, I would encourage you to check out the Department of Energy Water Power Technology Office website. A lot of interesting things happening in the US. And also check out the European Marine Energy Center website. It's emac.org.uk. A lot of exciting things happening there. In addition to the work that Oliver highlighted with Orbital Marine, there's quite a few other things going on there. And they have hydrogen projects oriented towards producing clean hydrogen from marine energy and wind energy. So a lot of interesting things happening on there. So that's it for the day. So just thank you for all of you for joining us on the first day of the workshop, and hopefully see you tomorrow morning, bright and early. And we've got a sneak peek of tomorrow's agenda that's on the screen now. And thank you very much.